Subscribe to the channel so you don't miss out on any of these videos. The cosmos is alive with mysteries, yet few are as strange and captivating as the unseen waves that ripple through space and stars. Imagine an invisible force weaving through the universe, moving plasma, the fourth state of matter, like wind sweeping across the ocean. These are Alfven waves, and they might just be the key to understanding how stars breathe, how solar storms erupt, and even how the fabric of interstellar space hums with unseen energy. But what are Alfven waves really? And why do they matter? The answers will take us on a journey deep into the heart of astrophysics, where magnetic fields, plasma, and oscillations interact in ways that are both fundamental and mind-bending. Plasma is often called the hidden majority of the universe, making up more than 99% of its visible matter. It's a state of matter like solid, liquid, or gas, but with a twist: its particles are electrically charged. This means that plasma isn't just influenced by gravity but dances to the tune of magnetic and electric forces. Alfven waves, named after the Swedish physicist Hannes Alfven who first theorized them in 1942, are oscillations in a plasma's magnetic field. Think of them as ripples in a pond, except the pond is a magnetic field, and the ripples are carried by plasma particles moving in concert with magnetic lines of force. Understanding Alfven waves begins with their environment, plasma. Unlike the predictable flow of water or air, plasma behaves chaotically. Charged particles in plasma, ions and electrons, are constantly interacting with magnetic and electric fields. These interactions create a feedback loop. Moving charges generate magnetic fields, which in turn influence the movement of the charges. When a disturbance, like a sudden change in magnetic pressure, occurs, it can send a wave rippling through the plasma. This wave is the Alfven wave, a disturbance that moves through the plasma by pushing and pulling magnetic field lines. The beauty of Alfven waves lies in their dual nature. On one hand, they are a physical phenomenon, a literal wave moving through plasma. On the other, they act as a messenger, carrying information about the magnetic and electric conditions of their environment. They can tell scientists about the density, temperature, and magnetic structure of the plasma they travel through, making them invaluable tools for studying everything from the Sun to distant galaxies. Take the Sun, for instance. Our star is a chaotic ball of plasma, its surface roiling with storms, flares, and eruptions. Scientists have long puzzled over why the Sun's corona, the outermost layer of its atmosphere, is so much hotter than its surface. This coronal heating problem defies common sense. Shouldn't the Sun's heat decrease as you move farther from its core? Alfven waves may hold the answer. As these waves propagate from the Sun's surface into its corona, they carry energy with them. This energy could be what heats the corona to its staggering temperatures, often millions of degrees hotter than the surface below. But the role of Alfven waves doesn't stop at heating. They are also thought to be key players in solar winds, the streams of charged particles that flow from the Sun into the solar system. These winds can disrupt satellites, interfere with radio communications, and even trigger auroras on Earth. Alfven waves may help accelerate these particles, pushing them to the high speeds observed in solar winds. By understanding these waves, scientists can better predict space weather and its effects on Earth, a field of study that is becoming increasingly important as our reliance on technology grows. Alfven waves aren't confined to the Sun, though. They are a universal phenomenon, present wherever plasma and magnetic fields coexist. This includes the magnetospheres of planets, the interstellar medium that fills the space between stars, and even the plasma that surrounds black holes. In Earth's magnetosphere, for example, Alfven waves can help explain how energy from the solar wind is transferred to our planet's magnetic field. This energy can drive phenomena like the auroras, creating breathtaking displays of light near the poles. In the interstellar medium, Alfven waves act as the threads of a cosmic tapestry, weaving together the magnetic fields and plasma that permeate space. They help to regulate the movement of charged particles and can even influence the formation of stars. When a cloud of gas and dust begins to collapse under its own gravity, magnetic fields and Alfven waves can slow the collapse, giving rise to the conditions necessary for a star to form. Without these waves, the process of star formation might look very different, or not happen at all. Even on the grandest scales, Alfven waves have a role to play. In the accretion disks that form around black holes, plasma spirals inward, heating up and emitting radiation as it falls. Alfven waves can transport energy and angular momentum within these disks, affecting how the plasma behaves and potentially influencing the growth of the black hole itself. Their presence in such extreme environments is a testament to their universality and importance. Despite their significance, Alfven waves remain challenging to study. They are invisible to the naked eye and often occur in environments that are difficult or impossible to observe directly. Instead, scientists rely on indirect methods, such as spacecraft measurements and computer simulations, to study these elusive waves. Missions like NASA's Parker Solar Probe and ESA's Solar Orbiter are designed to get up close and personal with the Sun, providing unprecedented data on its plasma and magnetic fields. These missions have already begun to shed light on the role of Alfven waves in solar phenomena, and future discoveries are sure to follow. The study of Alfven waves is not just about understanding the universe, it's about connecting the dots between its smallest and largest scales. These waves link the behavior of individual particles to the dynamics of stars, galaxies, and even the vast voids of interstellar space. They are a reminder that the universe is a deeply interconnected system, where even the smallest disturbances can have far-reaching effects. Alfven waves are more than just a scientific curiosity. They are a window into the complex, dynamic, and often surprising behavior of the universe. From the sun's corona to the depths of interstellar space, these magnetic oscillations are everywhere, shaping the cosmos in ways we are only beginning to understand. And as our knowledge grows, so too does our appreciation for the hidden forces that govern the universe, reminding us that even the most invisible phenomena can have profound impacts on the world around us. The intrigue of Alfven waves lies not only in their universal presence but also in their profound implications for how we understand energy transfer in space. Plasma, being the dominant form of matter in the universe, exists in a constant state of interaction with magnetic fields. These interactions are dynamic, giving rise to the mesmerizing dance of Alfven waves. To truly grasp their significance, we must delve deeper into the physics that underpins them and the broader consequences they impose on both cosmic and human scales. At their core, Alfven waves are governed by the principles of magnetohydrodynamics, MHD, a branch of physics that studies the behavior of electrically conducting fluids like plasma in the presence of magnetic fields. MHD equations describe how magnetic fields and plasma interact, creating a framework for understanding phenomena like Alfven waves. These waves arise when a magnetic field in a plasma is perturbed. This perturbation travels through the plasma, carrying energy along the magnetic field lines like a plucked guitar string vibrating along its length. The speed at which Alfven waves propagate depends on the strength of the magnetic field and the density of the plasma. Stronger magnetic fields and lower plasma densities allow for faster wave propagation. This variability in speed gives scientists a valuable diagnostic tool. By measuring the properties of Alfven waves, they can infer details about the magnetic field strength and plasma conditions in a given region. This is particularly useful for studying environments that are otherwise difficult to access, such as the sun's corona or the interstellar medium. One of the most fascinating aspects of Alfven waves is their role in energy transfer. In space, energy is not always evenly distributed. Magnetic fields, for example, can store enormous amounts of energy, which can be released in dramatic events like solar flares or magnetic reconnection. Alfven waves serve as conduits for this energy, transporting it across vast distances within plasmas. This energy transfer is not just a passive process but an active one, influencing the behavior of the plasma and the magnetic fields themselves. Consider the Sun once more. Its surface, or photosphere, is a turbulent place where magnetic fields are constantly shifting and interacting. These interactions create disturbances that propagate outward in the form of Alfven waves. As these waves move into the corona, they encounter less dense plasma and stronger magnetic fields, allowing them to carry significant amounts of energy. This energy can then be deposited in the corona, contributing to its extreme temperatures. The efficiency of this process is still a topic of active research, but it is clear that Alfven waves are a key piece of the puzzle. The implications of Alfven waves extend beyond heating and energy transfer. They also play a crucial role in particle acceleration, a process that is fundamental to many astrophysical phenomena. When Alfven waves propagate through a plasma, they can interact with charged particles, transferring energy to them. This can accelerate particles to high speeds, giving rise to phenomena like cosmic rays and solar energetic particles. These accelerated particles can have significant effects, from shaping planetary magnetospheres to posing hazards for astronauts and spacecraft. In the realm of planetary science, Alfven waves are equally impactful. Earth's magnetosphere, for example, is a dynamic region where solar wind plasma interacts with our planet's magnetic field. This interaction generates a variety of waves, including Alfven waves, which help to transfer energy and momentum within the magnetosphere. This energy transfer can drive geomagnetic storms, auroras, and other space weather phenomena. By studying Alfven waves in Earth's magnetosphere, scientists can better understand how our planet interacts with its space environment, leading to improved space weather forecasting. Moving beyond our solar system, Alfven waves are key to understanding the behavior of the interstellar medium. This vast expanse of space between stars is filled with a tenuous plasma threaded by magnetic fields. Alfven waves propagate through this medium, influencing the movement of charged particles and the dynamics of magnetic fields. They can help to dissipate energy, regulate turbulence, and even influence the distribution of cosmic rays. These processes are critical for understanding how stars and galaxies evolve over time. Even in the most extreme environments, such as the plasma surrounding black holes, Alfven waves make their presence known. In these regions, the intense gravitational and magnetic forces create conditions that are difficult to replicate on Earth. Alfven waves can play a role in transporting energy and angular momentum, influencing the behavior of the plasma and the growth of the black hole. These waves may also contribute to the generation of powerful jets of plasma that are often observed emanating from active galactic nuclei, some of the brightest objects in the universe. As our understanding of Alfven waves grows, so too does our ability to harness their properties for practical applications. One area of interest is fusion energy, where plasma is confined and heated to conditions necessary for nuclear fusion. Alfven waves could be used to control and stabilize the plasma, improving the efficiency of fusion reactors. This potential application highlights the deep connection between the study of space and the pursuit of technological advancements on Earth. The journey of Alfven waves from theoretical concept to cornerstone of astrophysics is a testament to the power of scientific curiosity and innovation. Hannes Alfven's groundbreaking work not only earned him a Nobel Prize in physics but also laid the foundation for decades of research that continues to uncover the secrets of these magnetic oscillations. Each discovery adds a new layer to our understanding, revealing a universe that is as interconnected as it is awe-inspiring. What makes Alfven waves particularly compelling is their universality. They are not confined to a single environment or phenomenon but are a fundamental feature of plasma behavior. Whether it's the Sun's corona, Earth's magnetosphere, the interstellar medium, or the plasma surrounding black holes, Alfven waves are there, shaping the cosmos in ways both subtle and profound. They remind us that the universe is a deeply interconnected system, where even the smallest disturbances can have far-reaching effects. In the grand scheme of things, Alfven waves are a reminder of the invisible forces that govern our universe. They are a testament to the complexity and beauty of the cosmos, a constant reminder that there is always more to discover. As we continue to explore the universe, both near and far, Alfven waves will remain a crucial piece of the puzzle, helping us to unlock the secrets of the stars and beyond. The vastness of the universe is a testament to its intricate mechanisms, and Alfven waves serve as one of the subtle yet profound threads weaving this cosmic tapestry together. These magnetic oscillations are not just theoretical abstractions. They are tangible, measurable phenomena that influence everything from the behavior of individual particles to the dynamics of entire galaxies. To truly appreciate their importance, it's necessary to delve even further into their mechanics, applications, and implications, both in space and on Earth. Alfven waves owe much of their behavior to the dual nature of plasma. Plasma, often called the fourth state of matter, is a soup of charged particles, electrons and ions, that move freely under the influence of electric and magnetic fields. This charged nature means that plasma doesn't simply react to magnetic fields, it actively shapes and is shaped by them. Alfven waves emerge from this dynamic relationship, a perfect interplay between the motion of the plasma and the structure of magnetic fields. The key feature of Alfven waves is their ability to propagate along magnetic field lines. These waves are transverse, meaning the motion of the plasma is perpendicular to the direction of the wave's propagation. This characteristic distinguishes Alfven waves from other types of plasma waves, such as sound waves, which are longitudinal. The transverse nature of Alfven waves allows them to carry energy and information efficiently, a quality that has profound implications for understanding and utilizing them. One of the fascinating aspects of Alfven waves is their ability to interact with particles in a plasma. This interaction is not just a passive exchange of energy. It can lead to resonance effects where the energy transfer becomes highly efficient. This resonance occurs when the frequency of the Alfven wave matches the natural frequency of the particles in the plasma. When this happens, particles can absorb energy from the wave, accelerating to high speeds. This process, known as wave-particle interaction, is a cornerstone of many astrophysical and laboratory plasma phenomena. In the context of space, wave-particle interactions play a critical role in shaping the environment. For instance, in the Earth's magnetosphere, Alfven waves can interact with charged particles trapped in the Van Allen radiation belts. This interaction can cause particles to gain energy, leading to phenomena like auroras. Similarly, in the solar wind, a stream of charged particles emanating from the sun, Alfven waves help to regulate the flow of energy and momentum, influencing how the solar wind interacts with planets and other celestial bodies. The role of Alfven waves in particle acceleration is particularly intriguing in the study of cosmic rays. Cosmic rays are high-energy particles that travel through space, originating from sources like supernovae, pulsars, and active galactic nuclei. The exact mechanisms by which these particles gain their incredible energies are still a topic of active research, but Alfven waves are thought to play a significant role. By interacting with particles in the turbulent environments of supernova remnants, or the accretion disks of black holes, Alfven waves can help to accelerate these particles to near light speeds. Another area where Alfven waves make their mark is in the study of turbulence. Turbulence is a chaotic, energy-dissipating process that occurs in many astrophysical plasmas, from the solar wind to the interstellar medium. Alfven waves contribute to this turbulence, breaking down large-scale motions into smaller ones and redistributing energy throughout the plasma. This process, known as the Alfvenic cascade, is a key mechanism for dissipating energy in space plasmas. Understanding this cascade is essential for explaining phenomena like coronal heating and the dissipation of energy in the interstellar medium. The study of Alfven waves has also led to advancements in understanding the solar corona, the Sun's outermost layer. The corona is incredibly hot, millions of degrees hotter than the Sun's surface, a phenomenon that has puzzled scientists for decades. Alfven waves are one of the leading candidates for explaining this so-called coronal heating problem. By carrying energy from the Sun's surface to the corona, Alfven waves can deposit their energy in the form of heat, helping to maintain the corona's extreme temperatures. In addition to their role in astrophysical phenomena, Alfven waves have practical applications closer to home. In the field of controlled nuclear fusion, scientists aim to replicate the processes that power the Sun to generate clean, virtually limitless energy. Alfven waves can be used to manipulate the plasma in fusion reactors, helping to stabilize it and improve energy confinement. This application highlights the deep connection between fundamental science and technological innovation, showing how the study of space can have direct benefits for humanity. Alfven waves also provide valuable insights into the behavior of plasma in laboratory experiments. By studying these waves under controlled conditions, scientists can test theories of plasma physics and refine their understanding of how plasma interacts with magnetic fields. These experiments not only advance our knowledge of space plasmas but also have applications in industries ranging from telecommunications to medicine. The universality of Alfven waves is a reminder of the interconnected nature of the universe. These waves are not confined to a single environment, or scale but are a fundamental aspect of plasma behavior across the cosmos. From the smallest laboratory experiments to the largest galactic structures, Alfven waves are a constant presence, shaping the dynamics of plasmas and magnetic fields. The more we study Alfven waves, the more questions arise. How do they interact with other types of waves in a plasma? What role do they play in the formation of magnetic structures like filaments and loops? How do they influence the evolution of galaxies and the large-scale structure of the universe? These questions drive ongoing research, pushing the boundaries of our understanding and opening new avenues of exploration. Ultimately, Alfven waves are a testament to the beauty and complexity of the universe. They are a reminder that even the most subtle phenomena can have profound implications, shaping the cosmos in ways that are both intricate and awe-inspiring. As we continue to explore the mysteries of space, Alfven waves will remain a key piece of the puzzle, helping us to unlock the secrets of the universe and our place within it. The story of Alfven waves is far from complete. As we peel back the layers of this fascinating phenomenon, we uncover even more connections to the broader dynamics of space, energy, and the physical laws that govern the universe. These waves are more than a scientific curiosity. They are a fundamental feature of how magnetic fields and plasma interact, a relationship that underpins countless phenomena across the cosmos. One area where Alfven waves have recently gained attention is in their potential to explain mysterious fluctuations in the intergalactic medium. The intergalactic medium, the sparse material that exists between galaxies, is primarily composed of plasma. This plasma, though incredibly diffuse, is threaded with magnetic fields that extend across vast distances. Alfven waves are thought to traverse these magnetic fields, carrying energy and potentially contributing to the thermal state and structure of the intergalactic medium. These waves may also help to explain the magnetization of space over cosmic timescales, a phenomenon that has long puzzled astrophysicists. Another frontier in the study of Alfven waves lies in understanding their role in magnetic reconnection. Magnetic reconnection is a process where magnetic field lines break and reconnect, releasing enormous amounts of energy. This process occurs in a variety of settings, from solar flares and coronal mass ejections to the magnetospheres of planets. Alfven waves are believed to play a role in facilitating magnetic reconnection by transporting energy and information through plasma, making the process more dynamic and complex. This insight is critical for understanding space weather, which can have significant effects on satellites, communication systems, and power grids on Earth. Alfven waves are also being explored as a tool for probing the interiors of celestial bodies. In the Sun, for instance, these waves can penetrate deep into the solar atmosphere, providing clues about the Sun's magnetic field structure and dynamics. By studying how Alfven waves propagate through different layers of the Sun, scientists can gain a better understanding of solar processes, including the generation of the Sun's magnetic field through dynamo action. This knowledge is essential for predicting solar activity and its potential impact on Earth. Moreover, Alfven waves could offer insights into the behavior of plasma in exotic environments like neutron stars and black hole accretion disks. Neutron stars, with their intense magnetic fields and dense plasma environments, are natural laboratories for studying the interplay of plasma and magnetism under extreme conditions. Alfven waves could help to explain phenomena such as pulsar winds and magnetar flares, shedding light on the physics of these enigmatic objects. Similarly, in the chaotic accretion disks surrounding black holes, Alfven waves may contribute to angular momentum transport and energy dissipation, influencing how matter falls into these gravitational wells. As our observational tools improve, the ability to detect and analyze Alfven waves in space has become more precise. Missions like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are providing unprecedented data on the Sun's atmosphere and solar wind, allowing scientists to observe Alfven waves in action. These missions are revealing how these waves interact with the solar plasma, transporting energy and influencing the dynamics of the Sun's magnetic field. This information is invaluable for constructing more accurate models of the solar wind and its interaction with the heliosphere, the vast bubble of charged particles and magnetic fields surrounding our solar system. The exploration of Alfven waves is also being advanced by sophisticated computer simulations. These simulations allow scientists to recreate the conditions of space plasmas and study the behavior of Alfven waves in detail. By modeling how these waves propagate, interact, and dissipate energy, researchers can test hypotheses and refine their understanding of plasma physics. These simulations are crucial for bridging the gap between theory and observation, providing a virtual laboratory for studying phenomena that are otherwise difficult or impossible to observe directly. Beyond their scientific significance, Alfven waves inspire profound philosophical questions about the nature of the universe. These waves are a manifestation of the fundamental forces that govern matter and energy, a tangible expression of the intricate interplay between magnetism and motion. They remind us that even in the vast emptiness of space, there is structure, order, and a kind of cosmic rhythm that connects everything. As we continue to study Alfven waves, we are not just uncovering the mechanics of plasma and magnetic fields, we are also deepening our understanding of the universe's interconnectedness. These waves are a bridge between the microscopic and the macroscopic, between the particle-level interactions in plasma and the large-scale dynamics of galaxies and interstellar space. They highlight the elegance of the physical laws that govern the cosmos, revealing a universe that is as beautiful as it is complex. The journey to fully understand Alfven waves is still in its early stages. New discoveries and insights are constantly emerging, driven by advances in technology, observation, and theory. Each breakthrough adds another layer to our understanding, bringing us closer to answering some of the most fundamental questions about the universe. What role do Alfven waves play in the evolution of galaxies? How do they influence the formation of stars and planetary systems? Can we harness their properties to solve practical challenges here on Earth? In many ways, the study of Alfven waves exemplifies the essence of scientific inquiry, a relentless pursuit of knowledge, fueled by curiosity and the desire to understand the world around us. These waves are not just a topic of academic research, they are a window into the universe's inner workings, a glimpse into the forces that shape our reality. The story of Alfven waves is a reminder that even the smallest and most subtle phenomena can have profound implications. They teach us that the universe is not a static, unchanging void but a dynamic, living entity, full of movement, energy, and complexity. And as we continue to explore these magnetic oscillations, we are not just learning about the universe, we are also learning about ourselves and our place in the grand cosmic scheme. The potential of Alfven waves to reshape our understanding of space and plasma physics cannot be overstated. Their study offers insights not only into cosmic structures but also into the processes that drive the very life cycles of stars and the creation of the elements that make up our universe. But this journey is far from straightforward. The behavior of Alfven waves can be both predictable and enigmatic, driven by subtle variations in their environment and interactions with other waves and forces. A key challenge in understanding Alfven waves lies in the sheer complexity of plasma as a state of matter. Unlike solids, liquids, or gases, plasma is a charged medium where electromagnetic forces dominate. This means that the behavior of particles in a plasma is influenced not only by collisions and thermal motion, but also by the ever-changing magnetic and electric fields around them. Alfven waves arise from this interplay, propagating through plasma by coupling the motion of particles to the oscillations of magnetic fields. One of the remarkable features of Alfven waves is their ability to transport energy over vast distances without significant dissipation. In the vacuum of space, where collisions between particles are rare, Alfven waves can travel nearly undisturbed for thousands, even millions of kilometers. This property makes them a crucial mechanism for transferring energy from one region of space to another. For example, Alfven waves generated by solar activity can carry energy outward through the solar wind, influencing the behavior of planetary magnetospheres and the interstellar medium. However, this efficient energy transfer can also lead to intriguing consequences. In certain conditions, Alfven waves can become unstable, leading to the growth of turbulence in the plasma. This turbulence, in turn, can cause the waves to break down into smaller-scale oscillations, creating a cascade of energy across different scales. This process, known as wave-particle interaction, is thought to play a crucial role in heating the solar corona and accelerating the solar wind. The phenomenon of wave-particle interaction highlights one of the most exciting aspects of Alfven waves: their ability to interact with charged particles and plasma. When the frequency of an Alfven wave matches the natural frequency of a particle's motion, energy can be transferred between the wave and the particle. This resonant interaction can cause particles to gain energy, accelerating them to high speeds. This mechanism is believed to be responsible for the acceleration of cosmic rays, the high-energy particles that bombard Earth from space. Cosmic rays provide a fascinating link between Alfven waves and some of the most energetic phenomena in the universe. These particles, which originate from sources such as supernovae and active galactic nuclei, are accelerated to near-light speeds by shock waves and magnetic fields in plasma. Alfven waves, with their ability to propagate through magnetic fields and interact with particles, are thought to play a key role in this process. By studying how these waves operate, scientists hope to uncover the origins of cosmic rays and their impact on the universe. Another area where Alfven waves are making waves, pun intended, is in the study of planetary magnetospheres. The magnetic fields of planets like Earth and Jupiter are surrounded by plasma environments shaped by the interaction of the planet's magnetic field with the solar wind. Alfven waves are a key component of this interaction, carrying energy and information between different regions of the magnetosphere. On Earth, these waves are associated with auroras, the spectacular light displays caused by the collision of charged particles with the atmosphere. Jupiter's magnetosphere, the largest in the solar system, provides a particularly intriguing case study. The planet's magnetic field interacts with its volcanic moon Io, creating a plasma torus that emits powerful Alfven waves. These waves travel along Jupiter's magnetic field lines, connecting Io to the planet's polar regions. By studying these waves, scientists can gain insights into the dynamics of Jupiter's magnetosphere and the processes that drive its intense radiation belts. The role of Alfven waves extends even to the edges of our solar system, where the solar wind interacts with the interstellar medium. The boundary of the heliosphere, known as the heliopause, marks the point where the influence of the Sun's magnetic field and solar wind gives way to the interstellar environment. Alfven waves are thought to play a crucial role in this interaction, influencing the structure and dynamics of the heliopause. By studying these waves, missions like Voyager 1 and 2 are providing a glimpse into the complex processes that govern the boundaries of our solar system. The potential applications of Alfven waves are not limited to space. On Earth, researchers are exploring their use in advanced technologies such as fusion energy. In experimental fusion reactors like tokamaks, plasma is confined and heated by magnetic fields to create conditions similar to those in the Sun. Alfven waves could play a role in stabilizing the plasma and transferring energy, making them a valuable tool for achieving sustainable nuclear fusion. Despite the progress we've made in understanding Alfven waves, many questions remain unanswered. What triggers the generation of these waves in different astrophysical settings? How do they evolve over time, and what determines their stability? How do they interact with other types of waves and particles in plasma? These questions drive ongoing research, pushing the boundaries of what we know about the universe. The study of Alfven waves is a testament to the interconnectedness of science. It draws on principles from physics, astronomy, and mathematics, weaving them together to create a deeper understanding of the cosmos. It also highlights the importance of curiosity and exploration, reminding us that even the most abstract phenomena can have profound implications for our understanding of the universe. As we continue to probe the mysteries of Alfven waves, we are reminded of the vastness and complexity of the universe. These magnetic oscillations are not just a scientific curiosity, they are a key to understanding the forces that shape stars, galaxies, and the very fabric of space itself. Their study is a journey into the heart of the cosmos, a quest to uncover the hidden rhythms that govern the universe. The study of Alfven waves opens a gateway to many of the universe's most profound mysteries. These waves are intricately tied to the processes shaping not only stars and interstellar space but also the evolution of galaxies. Their ability to mediate energy transfer, influence magnetic field structures, and interact with charged particles places them at the heart of some of the most dynamic phenomena in the cosmos. However, To truly appreciate the scope of Alfven waves, we must dive deeper into their complex behaviors and applications in both astrophysics and plasma physics. A fascinating aspect of Alfven waves is their dual nature. They are simultaneously simple in their fundamental principles and extraordinarily complex in their behavior. Alfven waves are born from the interaction of magnetic fields and charged particles in a plasma. On paper, this interaction may seem straightforward, but the real-world scenarios in which these waves operate are anything but simple. Space plasmas, whether in the solar wind, planetary magnetospheres, or intergalactic media, are highly dynamic and nonlinear systems. This means that Alfven waves, while governed by relatively simple equations, can exhibit behaviors that are difficult to predict and analyze. For instance, Alfven waves can interact with one another, leading to phenomena like wave coupling and energy cascading. In some cases, the energy of larger Alfven waves can transfer to smaller waves, a process that contributes to turbulence in the plasma. This turbulence is not just a random chaotic state. It has a structured nature that scientists are working hard to understand. Turbulence driven by Alfven waves plays a critical role in heating plasmas and accelerating particles, particularly in the solar corona and interstellar medium. The solar corona, the outermost layer of the Sun's atmosphere, provides a striking example of the importance of Alfven waves. Despite being farther from the Sun's surface, the corona is significantly hotter than the layers below it, a perplexing observation that defies simple explanations. Alfven waves are one of the leading candidates for solving this mystery. By carrying energy from the Sun's surface to the corona, these waves may provide the heat necessary to maintain the corona's extreme temperatures. However, the exact mechanism of energy transfer remains an active area of research. Do Alfven waves dissipate their energy gradually through interactions with particles in the corona? Or do they trigger localized bursts of energy release? These are the kinds of questions driving solar physics research today. The interstellar medium, the vast expanse of plasma, gas, and dust between stars, offers another arena where Alfven waves play a pivotal role. Here, these waves influence the dynamics of the magnetic fields that thread through galaxies. Magnetic fields in the interstellar medium are not static. They are constantly being stretched, twisted, and amplified by processes like star formation and supernova explosions. Alfven waves help mediate these processes, transporting energy and redistributing magnetic field structures. Without them, the interstellar medium's magnetic fields would lack the dynamic behavior necessary to support many of the phenomena we observe on cosmic scales. Moreover, Alfven waves are intimately connected to the formation of stars and planets. In star-forming regions, dense clouds of gas and plasma collapse under the influence of gravity. However, this collapse is not purely gravitational. Magnetic fields and Alfven waves also play critical roles. The waves help regulate the rate of collapse by redistributing angular momentum and energy. This ensures that the process of star formation proceeds in a controlled manner rather than in a chaotic collapse. Similarly, in protoplanetary disks of gas and dust that surround young stars, Alfven waves influence the motion of charged particles, shaping the conditions under which planets form. Even on the largest scales, Alfven waves leave their imprint. Galaxy clusters, the largest gravitationally bound structures in the universe, contain vast amounts of plasma permeated by magnetic fields. Alfven waves propagate through these plasmas, contributing to their turbulent motions and influencing the distribution of magnetic energy. These dynamics, in turn, affect the evolution of galaxies within the clusters. By studying Alfven waves in this context, scientists gain insights into the interplay between plasma physics and cosmology. Back on Earth, Alfven waves also hold promise for advancing technologies. In fusion research, where scientists aim to replicate the energy-generating processes of the Sun, controlling plasma behavior is a significant challenge. Alfven waves offer a potential solution. By manipulating these waves, researchers can stabilize plasma and optimize energy transfer within experimental reactors. This application of Alfven waves bridges the gap between cosmic phenomena and human-engineered systems, showcasing the versatility of these magnetic oscillations. Another terrestrial application lies in understanding and predicting space weather. The interaction of solar wind plasma with Earth's magnetic field generates Alfven waves, which can influence the behavior of charged particles in the magnetosphere. These particles, in turn, can pose risks to satellites, power grids, and communication systems. By studying Alfven waves, scientists aim to improve space weather forecasting, mitigating the potential impacts of solar storms on our technology-dependent society. Despite the advances made in understanding Alfven waves, much remains to be discovered. Observations from missions like NASA's Parker Solar Probe and ESA's Solar Orbiter are providing new data on the behavior of Alfven waves in the solar wind and corona. These missions are helping scientists refine their models and explore new phenomena, such as the role of Alfven waves in driving solar eruptions and particle acceleration. In the laboratory, experiments using high-energy plasma devices are pushing the boundaries of what we know about Alfven waves. By recreating the conditions of space plasmas, these experiments allow researchers to study the waves in controlled settings, shedding light on their fundamental properties and behaviors. The insights gained from these studies are feeding back into our understanding of space physics, creating a virtuous cycle of discovery. The journey of understanding Alfven waves is a testament to the power of curiosity and the interconnectedness of scientific disciplines. From the smallest scales of particle motion to the vast expanses of intergalactic space, these waves reveal the hidden structures and dynamics that govern the universe. They remind us that even the most abstract phenomena can have far-reaching implications, connecting the cosmos to our everyday lives. As we continue to study Alfven waves, we are not just uncovering the mysteries of magnetic oscillations in plasma. We are also expanding our understanding of the universe itself. The legacy of Hannes Alfven, who first theorized these waves, lives on in the work of countless scientists, pushing the boundaries of what we know and inspiring us to ask new questions. Alfven waves are more than just a scientific phenomenon. They are a symbol of humanity's relentless quest to understand the cosmos. The study of Alfven waves continues to redefine our understanding of the universe, providing insights into some of the most fundamental questions about energy, magnetism, and plasma dynamics. As we dive even deeper into their role across cosmic phenomena, we uncover layers of complexity that reveal just how intertwined these waves are with the fabric of the cosmos. One of the most intriguing aspects of Alfven waves lies in their role in particle acceleration, a process critical to the energetic phenomena observed throughout the universe. From the auroras dancing in Earth's polar skies to the powerful jets emitted by black holes, particle acceleration is a fundamental mechanism that links small-scale plasma behavior to large-scale astrophysical events. Alfven waves are key players in this process. They can transfer their energy to charged particles in a plasma, propelling them to high velocities. This mechanism, known as wave-particle interaction, is central to the generation of cosmic rays and the energetic particles that populate the interstellar medium. In Earth's magnetosphere, for example, Alfven waves interact with electrons and ions, accelerating them along magnetic field lines. This acceleration process contributes to the auroras, stunning displays of light caused by particles colliding with the upper atmosphere. These waves not only enhance our appreciation of natural beauty, but also offer a glimpse into the intricate dynamics of space plasma. By studying the interaction of Alfven waves with particles in Earth's magnetosphere, scientists gain a better understanding of space weather phenomena and their potential impact on technology and human activity. Alfven waves also play a crucial role in the generation and maintenance of cosmic magnetic fields. Magnetic fields are ubiquitous in the universe, threading through galaxies, stars, and even interstellar space. However, their origin and evolution remain one of the most significant mysteries in astrophysics. Alfven waves contribute to the dynamo processes that amplify and sustain magnetic fields over time. In stars, for instance, the interaction between Alfven waves and convective motions in the stellar plasma helps generate and stabilize magnetic fields, influencing stellar activity cycles and phenomena like sunspots. In the broader context of galaxy formation, Alfven waves influence the behavior of magnetic fields in the intergalactic medium, the vast, tenuous plasma that exists between galaxies. These fields play a role in shaping the motion of charged particles and affect the distribution of energy and matter on cosmic scales. By understanding how Alfven waves propagate and interact in such environments, scientists can refine models of galaxy evolution and uncover the processes that govern large-scale structures in the universe. One particularly exciting area of research is the role of Alfven waves in the mysterious phenomenon of plasma heating. Plasmas in the universe often exhibit temperatures far higher than would be expected based on their energy sources alone. This discrepancy, known as the heating problem, is observed in contexts ranging from the solar corona to accretion disks around black holes. Alfven waves are thought to be a crucial piece of the puzzle. As they propagate through plasma, these waves can transfer energy to smaller-scale fluctuations, ultimately dissipating as heat. This process, while conceptually simple, involves complex interactions that are still not fully understood. In the solar corona, for instance, Alfven waves are believed to carry energy from the Sun's surface into its outer atmosphere. As these waves encounter the highly dynamic plasma environment of the corona, they undergo processes like resonance and turbulent dissipation, converting their energy into heat. Observations from space missions and ground-based telescopes continue to shed light on this phenomenon, but many questions remain. How efficiently do Alfven waves transfer energy to the plasma? What specific conditions favor their dissipation? These are active areas of research that promise to deepen our understanding of solar and stellar physics. Moving beyond the Sun, Alfven waves also influence the behavior of plasmas in accretion disks, rotating structures of gas and plasma that surround compact objects like black holes, neutron stars, and white dwarfs. These disks are some of the most extreme environments in the universe, with intense gravitational forces and magnetic fields shaping their dynamics. Alfven waves propagate through the plasma in accretion disks, redistributing angular momentum and contributing to the turbulent motions that drive accretion. Without these waves, the flow of material onto the central object would be far less efficient, altering the behavior of phenomena like X-ray emissions and relativistic jets. In recent years, the study of Alfven waves has been revolutionized by advancements in observational technology and computational modeling. Space missions like the Parker Solar Probe and Solar Orbiter have provided unprecedented views of the Sun's plasma environment, revealing new details about the behavior of Alfven waves in the solar wind and corona. These observations have confirmed many theoretical predictions while also raising new questions about the interactions between waves, particles, and magnetic fields. On the computational front, sophisticated simulations allow researchers to model the propagation of Alfven waves in realistic plasma environments. These models capture the nonlinear interactions and turbulence that characterize many plasma systems, offering insights that are difficult to obtain from observations alone. By combining observational data with computational models, scientists are building a more comprehensive picture of how Alfven waves operate across a wide range of astrophysical contexts. Despite these advances, there is still much to learn about the broader implications of Alfven waves. Their influence extends beyond individual stars or galaxies, touching on some of the most profound questions in cosmology. For example, Alfven waves may play a role in the early universe, influencing the distribution of magnetic fields during the formation of the first stars and galaxies. They could also provide clues about the mysterious dark matter and dark energy that dominate the universe's composition, offering new perspectives on the forces shaping cosmic evolution. As our understanding of Alfven waves deepens, so too does our appreciation for the interconnectedness of the universe. These waves, born from the simple interaction of magnetic fields and plasma, are a testament to the elegance and complexity of the cosmos. They remind us that even the most fundamental physical phenomena can have far-reaching implications, shaping the behavior of systems across vast scales of time and space. In many ways, the study of Alfven waves represents the spirit of scientific exploration. It is a journey that spans disciplines, from the physics of charged particles to the dynamics of galaxies. It challenges us to think deeply about the forces that govern the universe and inspires us to continue seeking answers to the questions that have driven humanity for centuries. As we continue to unlock the secrets of Alfven waves, we are not just learning about the universe, we are learning about our place within it. These magnetic oscillations, which govern the behavior of plasma in stars, galaxies, and beyond, are a reminder of the power of curiosity and the boundless potential of human discovery. Alfven waves are far more than just a scientific curiosity. They are fundamental to understanding how energy, matter, and magnetic fields interact in the universe. As we continue this exploration, the implications of their behavior and influence touch on nearly every aspect of astrophysics and plasma physics. A critical component of Alfven wave dynamics lies in their nonlinear behavior. While much of the initial theoretical work on these waves considered linear systems, where the response of the plasma is directly proportional to the force exerted, real-world plasmas are anything but linear. In environments like the solar corona, interstellar medium, or even fusion reactors on Earth, the interactions between waves and particles quickly lead to nonlinear phenomena. These include wave-wave interactions, wave-particle trapping, and turbulence, all of which add layers of complexity to their study. Nonlinear Alfven waves can generate a cascade effect, transferring energy from larger-scale waves to progressively smaller scales. This cascading process, often associated with turbulence, is critical for energy dissipation in many plasma systems. In astrophysical contexts, it is this dissipation that converts the energy carried by Alfven waves into heat, fueling processes like coronal heating or the warming of interstellar clouds. Understanding this cascade requires a detailed analysis of how waves of different frequencies and wavelengths interact, and it's an area where modern computational methods have proven invaluable. In interstellar space, where magnetic fields are weaker and plasma densities lower than in stars or the solar wind, Alfven waves exhibit different propagation characteristics. The low-density environment allows these waves to travel vast distances without significant energy loss. This makes them important for the transport of energy and momentum across the galaxy. For instance, Alfven waves generated by supernova explosions or galactic collisions can influence the dynamics of entire regions of the interstellar medium, driving shocks, and triggering star formation in dense molecular clouds. Alfven waves are also thought to contribute to the mysterious phenomenon of magnetic reconnection. This process, where magnetic field lines break and reconnect, is a key mechanism for releasing stored magnetic energy. Magnetic reconnection occurs in various environments, from the Sun's corona to Earth's magnetosphere, and it plays a role in explosive events like solar flares and coronal mass ejections. Alfven waves may help initiate or sustain reconnection by perturbing the magnetic field and plasma in localized regions. This connection between Alfven waves and reconnection is an active area of research, with significant implications for both astrophysics and space weather prediction. In the context of planetary magnetospheres, Alfven waves are instrumental in understanding how planets interact with their surrounding space environment. For example, Jupiter's magnetosphere, the largest and most powerful in the solar system, is a dynamic system driven by interactions with the solar wind and the planet's rotation. Alfven waves propagate along Jupiter's magnetic field lines, linking the planet's atmosphere to its moons. These waves help transfer energy and particles between regions, influencing phenomena like Jupiter's intense auroras and the radiation belts surrounding the planet. Even beyond our solar system, Alfven waves are likely at work in the magnetospheres of exoplanets, shaping their interactions with host stars. As we discover more exoplanets with magnetic fields, understanding how Alfven waves operate in these distant systems will become increasingly important. They could provide clues about the habitability of exoplanets by influencing their atmospheres and protecting them from stellar winds. One particularly exciting area of exploration involves the potential role of Alfven waves in the universe's earliest moments. During the epoch of recombination, when the first atoms formed and the cosmic microwave background radiation was released, magnetic fields and plasma dynamics may have played a role in shaping the structure of the universe. Alfven waves, if present, could have influenced the distribution of matter and energy during this critical period, leaving subtle imprints that we can detect today. In modern cosmology, researchers are investigating how Alfven waves might interact with dark matter and dark energy, the enigmatic components that make up most of the universe's mass and energy. While these phenomena are still poorly understood, studying their potential interplay with plasma dynamics could open new avenues for understanding the universe's evolution. Alfven waves provide a framework for exploring these possibilities, bridging the gap between theoretical models and observational data. On Earth, Alfven waves have practical applications in advancing technology and addressing global challenges. In fusion energy research, understanding how Alfven waves propagate and interact with plasma is critical for optimizing the performance of devices like tokamaks and stellarators. These devices aim to replicate the conditions of stars to produce clean, sustainable energy. Alfven waves play a dual role in this context. They can either enhance plasma stability or contribute to instabilities that disrupt the fusion process. By studying their behavior, scientists hope to harness their potential for improving energy confinement and efficiency. In space exploration, Alfven waves are increasingly recognized as a tool for probing the environments of other planets and moons. For instance, missions to Jupiter's moon Europa or Saturn's moon Enceladus could use Alfven wave observations to study subsurface oceans and magnetic interactions. These waves act as natural messengers, carrying information about the physical conditions of their environments. By decoding the signals embedded in Alfven waves, scientists can learn about the properties of these distant worlds without direct sampling. The study of Alfven waves also holds promise for advancing our understanding of fundamental physics. By observing their behavior in extreme conditions, such as near black holes or in the high-energy environments of active galactic nuclei, researchers can test the limits of our theories of magnetohydrodynamics and plasma physics. These observations provide a unique laboratory for exploring phenomena that are impossible to replicate on Earth. As we look to the future, the potential for new discoveries about Alfven waves is immense. With the advent of more advanced space missions, ground-based observatories, and computational tools, the opportunities for studying these magnetic oscillations are greater than ever. Whether it's through unraveling the mysteries of plasma heating, exploring their role in cosmic magnetic fields, or understanding their impact on particle acceleration, Alfven waves will continue to be a focal point of scientific inquiry. They are a reminder of the universe's interconnectedness, a testament to how a phenomenon as seemingly simple as a wave can influence systems on every scale. From the smallest particles in a plasma to the largest structures in the cosmos, Alfven waves reveal the elegance and complexity of the physical laws that govern our existence. In studying them, we not only uncover the secrets of the universe but also deepen our appreciation for the intricate dance of forces that shape the world around us. The role of Alfven waves in shaping cosmic structures underscores their importance in astrophysics. These waves propagate along magnetic field lines, acting as a conduit for energy transfer between different regions of space. Their influence extends from microscopic interactions at the particle level to macroscopic dynamics that govern galaxies and intergalactic matter. One of the most intriguing applications of Alfven wave theory is in the study of galaxy formation. Magnetic fields are pervasive in galaxies, and their presence can significantly influence the movement of gas and plasma during galaxy evolution. Alfven waves, as carriers of magnetic energy, play a vital role in regulating the flow of matter within galactic structures. For example, during the formation of spiral galaxies, these waves may help align gas streams along magnetic field lines, influencing the characteristic patterns we observe in spiral arms. On a larger scale, Alfven waves are also integral to understanding the behavior of galaxy clusters, the largest gravitationally bound structures in the universe. These clusters are permeated by hot plasma and magnetic fields, and Alfven waves facilitate energy transfer within this plasma. They are thought to contribute to the heating of intracluster gas, preventing it from cooling and collapsing. This heating mechanism is essential for explaining the observed properties of galaxy clusters and their long-term stability. Another significant area where Alfven waves make their presence felt is in the study of cosmic rays. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. The origins and propagation of these particles are deeply connected to magnetic fields and Alfven waves. As cosmic rays move through the interstellar medium, they interact with Alfven waves, which can scatter them and alter their trajectories. This scattering process not only influences the distribution of cosmic rays but also helps explain their observed energy spectrum. Alfven waves also serve as a tool for probing the elusive nature of cosmic magnetic fields. Despite their ubiquity, the origins and evolution of magnetic fields in the universe remain poorly understood. By studying the propagation of Alfven waves, scientists can gain insights into the strength, structure, and dynamics of these fields. This information is crucial for unraveling the history of the universe, as magnetic fields likely played a role in shaping the formation of stars, galaxies, and large-scale cosmic structures. In the realm of heliophysics, Alfven waves are central to our understanding of the Sun and its influence on the solar system. The solar wind, a stream of charged particles emanating from the Sun, is permeated by these waves. Alfven waves in the solar wind modulate its speed, density, and temperature, affecting its interaction with planetary magnetospheres. Understanding these interactions is critical for predicting space weather events, such as geomagnetic storms, which can have significant impacts on Earth's technology and infrastructure. Moreover, Alfven waves are key to solving the enduring mystery of coronal heating. The Sun's outer atmosphere, or corona, is millions of degrees hotter than its surface, a paradox that has puzzled scientists for decades. Alfven waves are thought to transport energy from the Sun's interior to the corona, where it is dissipated as heat. However, the exact mechanisms by which this energy transfer and dissipation occur remain an active area of research. Advances in observational technology, such as the Parker Solar Probe and the Solar Orbiter, are providing new data that could shed light on this phenomenon. In planetary science, Alfven waves are not only relevant to understanding planetary magnetospheres but also play a role in atmospheric dynamics. For instance, in Venus's ionosphere, where the planet lacks a global magnetic field, induced magnetic fields interact with the solar wind, generating Alfven waves. These waves help drive the escape of atmospheric particles, influencing the long-term evolution of Venus's atmosphere. Similarly, on Mars, Alfven waves generated in localized magnetic regions contribute to atmospheric loss processes, shaping the planet's climate history. The study of Alfven waves has also led to advancements in laboratory plasma research. In controlled experiments, scientists can replicate the conditions of space plasmas and observe the behavior of these waves in real time. Such experiments provide valuable insights into fundamental plasma physics and help validate theoretical models. For example, laboratory studies have revealed how Alfven waves interact with charged particles, leading to phenomena like Landau damping, where the energy of the wave is transferred to particles moving at the wave's phase velocity. These experiments are not only important for astrophysical research, but also have practical applications. In fusion energy research, Alfven waves are used to control plasma behavior in tokamaks and other experimental reactors. By manipulating these waves, scientists can improve energy confinement and stability, bringing us closer to achieving sustainable nuclear fusion, a potential game-changer for global energy needs. In space exploration, Alfven wave research is opening new avenues for understanding the environments of distant celestial bodies. For instance, missions to study the icy moons of Jupiter and Saturn could use Alfven wave observations to infer the properties of subsurface oceans and magnetic interactions. Similarly, future missions to exoplanets may rely on Alfven wave data to characterize their magnetic environments and assess their potential habitability. The implications of Alfven wave research extend even further into the realm of fundamental physics. These waves provide a unique framework for exploring the interplay between magnetic fields, plasma, and relativistic effects in extreme environments. For example, near black holes or neutron stars, where gravitational and magnetic forces reach unimaginable intensities, Alfven waves could reveal new physics beyond our current understanding. They might help explain phenomena like relativistic jets, which are streams of particles ejected at near-light speeds from the vicinity of black holes. As we delve deeper into the universe's mysteries, Alfven waves remain a powerful tool for uncovering the hidden dynamics of cosmic systems. Their ability to transfer energy, momentum, and information across vast distances makes them indispensable for understanding the universe's interconnected nature. They remind us that even the most fundamental processes, oscillations in a plasma, can have far-reaching consequences, shaping the cosmos in ways we are only beginning to comprehend. The future of Alfven wave research is bright, with new discoveries on the horizon. As technology advances and our observational capabilities expand, we can expect to uncover even more about these fascinating waves and their role in the universe. From unlocking the secrets of cosmic magnetic fields to enabling sustainable energy on Earth, the study of Alfven waves continues to push the boundaries of human knowledge. As we venture deeper into the cosmic realm, the importance of Alfven waves continues to unfold in surprising ways. These waves, though initially a theoretical concept, have now become a cornerstone in the field of astrophysics. Their ability to interact with plasma, manipulate magnetic fields, and influence energy distribution across vast distances makes them indispensable in understanding both the small-scale phenomena of stellar systems and the large-scale dynamics of galaxies and beyond. In particular, Alfven waves are crucial in explaining the behavior of plasma within the context of stellar atmospheres. The Sun's corona, for example, remains a significant puzzle due to its inexplicably high temperature compared to the solar surface. Alfven waves, traveling along the Sun's magnetic field lines, might carry energy from the deeper layers of the Sun's atmosphere, transferring it to the corona. This transfer of energy could be the key to resolving the long-standing mystery of coronal heating. As scientists continue to analyze data from solar missions like the Parker Solar Probe and Solar Orbiter, we're seeing promising developments in understanding how these waves work to sustain the corona's extreme temperatures. However, there's still a lot to learn. While the idea that Alfven waves are responsible for coronal heating has been around for decades, detailed measurements that support this theory have only recently begun to emerge. The study of Alfven waves could potentially redefine our understanding of solar physics, offering more insights into how the Sun produces such intense solar winds, and how these waves influence the behavior of charged particles around the Sun. If we understand how these waves contribute to the overall solar dynamics, it could help predict space weather patterns, an increasingly important task as we become more reliant on satellite technology and space-based infrastructure. In addition to their role in solar phenomena, Alfven waves have a profound impact on our understanding of astrophysical jets. These jets, which are seen in various cosmic objects like black holes, neutron stars, and even active galactic nuclei, are one of the most intriguing features in the universe. Some of the most powerful and energetic events in space are associated with these jets, and Alfven waves could be at the heart of them. These magnetic waves might play a critical role in collimating and accelerating particles to relativistic speeds, allowing them to be ejected in tightly focused beams. Understanding how Alfven waves facilitate this process could lead to breakthroughs in high-energy astrophysics and further our knowledge of the extreme environments around black holes and neutron stars. Additionally, Alfven waves have implications for the study of planetary magnetospheres, especially those of planets without substantial atmospheres or magnetic shields. Take Mars, for example. Though it lacks a global magnetic field, localized regions of magnetic anomalies exist, likely remnants of an ancient field. These magnetic fields interact with the solar wind, generating Alfven waves that may play a significant role in shaping the Martian ionosphere. The presence of these waves could help explain how Mars lost much of its atmosphere over billions of years, offering insights into planetary climate evolution on a broader scale. In the quest to understand the broader cosmos, Alfven waves also hold the key to understanding the movement and distribution of cosmic rays. These high-energy particles, which are accelerated to near-light speeds, are believed to have their origins in astrophysical phenomena such as supernova explosions or the powerful jets emanating from active galactic nuclei. The interaction between these particles and Alfven waves is critical in shaping their trajectories and energy levels. Alfven waves may act as a scattering agent for these cosmic rays, influencing their path across the universe. This interaction not only helps explain the observed distribution of cosmic rays but also provides crucial data on the nature of intergalactic magnetic fields. In galaxy clusters, Alfven waves are thought to be essential in regulating the distribution of gas and plasma, keeping the intergalactic medium from collapsing under its own gravity. When Alfven waves propagate through a plasma, they induce oscillations that can carry energy away from dense regions, preventing the gas from cooling and collapsing into stars. This effect may help maintain the balance of gas in galaxy clusters, keeping them in a relatively stable state over long periods of cosmic time. By studying these processes, scientists can better understand the mechanics behind galaxy formation and evolution. As we begin to map the magnetic landscapes of distant galaxies, Alfven waves provide an essential tool for exploring the magnetic fields that permeate these vast structures. Magnetic fields influence the motion of plasma, which in turn affects star formation, galactic dynamics, and even the shape of galaxies themselves. By investigating how Alfven waves propagate through these magnetic fields, we gain a better understanding of the underlying forces that govern the evolution of galaxies. This research could lead to new models of galaxy evolution that incorporate magnetic field dynamics more explicitly. Moreover, Alfven waves are integral to understanding how different types of space plasmas, like those in the interstellar medium, ISM, react to different forms of energy input. When supernovae explode, they release enormous amounts of energy that can compress and heat the surrounding plasma. Alfven waves are thought to be one of the mechanisms by which this energy spreads across the ISM. By studying these waves, we can better understand how energy from stellar death cycles is distributed and how it influences the interstellar medium's ability to form new stars. But Alfven waves are not limited to galactic or stellar environments. They also have the potential to reveal the fundamental properties of the universe at its most extreme. In environments near supermassive black holes or in the early universe, where both the gravitational and magnetic forces are intense, Alfven waves may act in ways we can only hypothesize. These waves could help unlock new theories about the early formation of the universe, or even offer insights into the quantum nature of space itself. As researchers continue to explore the intricacies of Alfven waves, technological advancements are likely to play a key role in shaping the next generation of discoveries. Instruments designed to probe the magnetic fields of distant cosmic objects, coupled with computational models that simulate wave propagation across vast distances, will allow for unprecedented levels of precision in understanding these waves. Additionally, the field of laboratory plasma physics will continue to contribute valuable data, as scientists work to replicate cosmic conditions on Earth and test theories about wave-particle interactions in controlled environments. The continued study of Alfven waves could also have practical applications here on Earth. Our understanding of these waves, and the energy transfer processes they facilitate, might one day be leveraged in the development of new technologies. For example, in the realm of space propulsion, Alfven waves could be harnessed to generate new forms of thrust, potentially opening the door to faster interplanetary travel. Similarly, the insights gained from studying Alfven waves in plasma could be applied to improve the design and efficiency of fusion reactors, which rely on plasma confinement to sustain nuclear fusion reactions. Looking to the future, the mysteries surrounding Alfven waves are only beginning to unfold. With continued research, we may uncover even more about their role in shaping the cosmos, from influencing star formation in distant galaxies to altering the course of energy across the universe. The study of these waves not only deepens our understanding of space but also challenges our perceptions of how fundamental forces, magnetic, gravitational, and energetic, interact across time and space. In the grand scheme of astrophysics, Alfven waves serve as a reminder that even the smallest of oscillations can have monumental effects. As the cosmic dance of plasma, magnetic fields, and energy continues across the universe, Alfven waves will remain at the forefront of our exploration, offering profound insights into the mechanisms that govern everything from the birth of stars to the behavior of galactic systems. The more we learn, the more we realize just how interconnected and dynamic the universe truly is. As we continue to unravel the mysteries surrounding Alfven waves, it's important to highlight how their role extends far beyond the realms of stars and galaxies. These magnetic oscillations influence phenomena at a much larger scale, from the behavior of cosmic structures to the very fabric of spacetime itself. Their study not only provides a window into the inner workings of the universe but also raises intriguing questions about the fundamental forces that govern it. One of the most significant contributions Alfven waves offer to our understanding is their potential connection to the behavior of black holes. Black holes are known for their extreme gravitational pull, warping the very fabric of spacetime around them. This warping can have profound effects on the behavior of plasma and electromagnetic fields in their vicinity, Alfven waves, which propagate along magnetic field lines, might provide an essential mechanism for the movement of energy around black holes. In particular, the role of these waves in transferring energy from the accretion disk, the hot, dense matter spiraling into a black hole, could be crucial in understanding how matter behaves in such extreme environments. In some cases, Alfven waves are thought to be responsible for the acceleration of particles in the relativistic jets ejected from supermassive black holes. These jets, which can travel at nearly the speed of light, are among the most energetic phenomena in the universe. It's believed that Alfven waves, by transferring energy along the magnetic field lines, can accelerate particles within these jets to velocities that approach the speed of light. This process helps explain the powerful energy emissions observed in active galactic nuclei and the high-energy radiation detected across vast distances. By exploring the role of Alfven waves in these systems, scientists can gain a deeper understanding of how black holes interact with their surroundings and how they influence the behavior of matter in the universe. Beyond black holes, Alfven waves are also crucial in understanding the behavior of galaxy clusters. These vast cosmic structures, which are made up of countless galaxies bound together by gravity, contain large amounts of hot, ionized gas. This plasma is often in a turbulent state, with magnetic fields threading through the gas and influencing its motion. Alfven waves, which propagate through this plasma, may serve as a mechanism for transferring energy between different parts of the cluster. They could help prevent the gas from cooling too quickly, which in turn might inhibit the formation of new stars. In this sense, Alfven waves could play a role in regulating the life cycle of galaxies within these clusters, influencing both star formation and the evolution of galactic structures over time. Furthermore, Alfven waves are not confined to just the visible universe. They may also provide valuable insights into the behavior of cosmic structures beyond our current observational reach. For example, in the early stages of the universe, when the cosmic plasma was in a hot, dense state, Alfven waves may have played a crucial role in the redistribution of energy across the cosmos. The interactions between magnetic fields and plasma during this time could have had a significant impact on the formation of the first stars and galaxies, providing a mechanism for energy transfer that helped shape the universe as we know it today. As we move to explore the role of Alfven waves in other cosmic phenomena, we begin to realize that they are intricately linked to the concept of cosmic magnetic fields. Magnetic fields are not only present around stars, planets, and black holes but also permeate vast stretches of intergalactic space. These fields, which stretch across enormous distances, interact with the plasma that fills the universe, giving rise to a wide variety of phenomena, including Alfven waves. The study of these waves provides an essential tool for understanding how magnetic fields influence the behavior of matter on a cosmic scale. One of the most fascinating aspects of Alfven waves is their potential to reveal new information about the origins of cosmic magnetic fields themselves. While the existence of magnetic fields in space has been well established, the exact mechanisms behind their creation and evolution remain a topic of ongoing research. Alfven waves, with their ability to propagate along magnetic field lines, may offer a clue as to how these fields are generated and sustained over time. By examining how Alfven waves interact with different types of magnetic fields, researchers may be able to uncover the fundamental processes that govern the creation of cosmic magnetic structures. Moreover, the study of Alfven waves in the context of interstellar and intergalactic plasma can shed light on the role that magnetic fields play in shaping the structure of the universe. Magnetic fields can influence the motion of plasma, leading to the formation of cosmic structures such as filaments, voids, and clusters. These structures are not only important for understanding the distribution of matter in the universe but also for grasping the larger cosmic dynamics that govern the behavior of galaxies and galactic clusters. Alfven waves, as an integral part of this magnetic interplay, provide a critical insight into how these structures evolve over time. As we continue to advance our understanding of Alfven waves, technological innovations will play a pivotal role in unlocking the full potential of these waves in astrophysical research. Current space missions, such as the Parker Solar Probe, are providing unprecedented data on the magnetic environment of the Sun, which will offer new insights into how Alfven waves propagate in stellar atmospheres. Similarly, advances in observational techniques, including the use of radio telescopes and space-based instruments, are allowing scientists to probe the magnetic fields and plasma in distant galaxies, providing a closer look at the role of Alfven waves in these systems. In the coming years, these advancements will likely lead to even more profound discoveries, as the interaction between plasma, magnetic fields, and Alfven waves becomes clearer. With new models and simulations, scientists will be able to refine their understanding of how Alfven waves shape the universe and influence the behavior of cosmic systems. These models, informed by observational data, will not only improve our knowledge of stellar and galactic phenomena but also enhance our ability to predict the behavior of cosmic systems in the future. At the same time, the continued study of Alfven waves will have far-reaching implications for other areas of research, particularly in the fields of plasma physics and space technology. In plasma research, understanding how waves like Alfven waves interact with charged particles can provide valuable insights into the behavior of plasma in laboratory settings, such as fusion reactors. The ability to manipulate Alfven waves could potentially lead to advances in fusion energy generation, offering a cleaner and more sustainable energy source for the future. Moreover, the lessons learned from studying Alfven waves in space could be applied to other areas of space exploration. For example, understanding how Alfven waves interact with plasma could be crucial in the design of spacecraft propulsion systems that rely on plasma as a driving force. By harnessing the principles of Alfven waves, we could develop new methods of propelling spacecraft at higher speeds, opening up the possibility of faster travel between planets and even star systems. The study of Alfven waves provides an essential piece of the puzzle in our understanding of the cosmos. These waves, though initially thought to be obscure and difficult to detect, are now recognized as a crucial mechanism for transferring energy, influencing plasma dynamics, and shaping cosmic structures. From the corona of the Sun to the farthest reaches of intergalactic space, Alfven waves are an integral part of the universe's functioning, offering profound insights into everything from star formation to black hole activity. As our observational tools and theoretical models continue to evolve, the mysteries surrounding Alfven waves will no doubt become clearer. In doing so, we will not only gain a deeper understanding of the forces that govern the universe but also unlock new possibilities for technology and space exploration. The journey to fully comprehend Alfven waves is still in its early stages. But as we delve deeper into the magnetic realms of the cosmos, it's clear that these waves hold the key to many of the universe's most profound secrets. As we continue to explore the many facets of Alfven waves, it becomes increasingly clear how their influence extends beyond just the immediate magnetic fields around stars and black holes. The complex relationship between magnetic fields and plasma across the universe suggests that Alfven waves are deeply embedded in the fabric of cosmic processes. These waves provide not only a method of energy transfer but also a means of communication between different cosmic systems, facilitating interactions that are vital to the structure and evolution of the universe. One of the lesser-known but important roles that Alfven waves play is in the regulation of space weather. Space weather refers to the dynamic conditions in space caused by the Sun's activity, including solar flares and coronal mass ejections. These events can release enormous amounts of energy into the surrounding space, which can then interact with Earth's magnetic field and cause geomagnetic storms. Alfven waves are thought to be involved in these processes by mediating the energy flow from the Sun to Earth. Understanding how Alfven waves interact with the solar wind could lead to better predictions of space weather events, which could have far-reaching consequences for satellite communications, GPS systems, and even power grids on Earth. The Sun itself, as the source of much of the plasma in our solar system, is an excellent laboratory for studying Alfven waves. In the Sun's outer layers, known as the corona, the plasma is heated to millions of degrees. One of the unsolved mysteries surrounding the Sun is why the corona is so much hotter than the surface of the Sun, which is only around 5,500 degrees Celsius. Alfven waves may hold the key to unlocking this mystery. These waves are thought to carry energy from the Sun's interior to the outer layers, transferring heat to the corona in a process known as wave heating. By understanding how Alfven waves contribute to the heating of the sun's corona, scientists hope to gain a better understanding of solar phenomena like solar flares, coronal mass ejections, and the behavior of the solar wind. Alfven waves are also integral to understanding the dynamics of the heliosphere, the bubble of charged particles that surrounds our solar system. This region, dominated by the solar wind, is affected by both the sun's activity and the interstellar medium. The interaction between Alfven waves and the solar wind helps regulate the movement of plasma within the heliosphere, influencing how charged particles are distributed across vast distances. As these waves travel outward from the sun, they can impact the behavior of the solar wind, including its speed and density, as well as the magnetic field lines that thread through the heliosphere. This dynamic process not only affects space weather but also contributes to the protection of our planet from high-energy cosmic radiation. When we extend our study of Alfven waves to other stars, we begin to see how these waves might influence the behavior of stellar winds. Just as the sun emits a steady stream of particles known as the solar wind, other stars also produce their own stellar winds. These winds can carry away mass from stars over time, influencing their evolution and lifespan. Alfven waves may play a role in shaping the intensity and behavior of these stellar winds, transferring energy and momentum to the particles that make up the wind. This interaction could affect everything from the formation of planetary systems to the ultimate fate of stars. Understanding how Alfven waves contribute to the dynamics of stellar winds is an important step in comprehending stellar evolution on a larger scale. In addition to their role in stars, Alfven waves have important implications for our understanding of the interstellar medium, ISM, the matter that fills the space between stars and a galaxy. The ISM is composed of gas and dust, much of it ionized, and is threaded through with magnetic fields. Alfven waves, propagating along these magnetic fields, serve as a mechanism for transferring energy across the ISM, influencing the movement and behavior of the gas within galaxies. These waves may help regulate the formation of stars by preventing the gas from cooling too quickly, thereby affecting the rate of star formation. Alfven waves could also contribute to the dynamics of cosmic dust, helping to shape the distribution of elements and molecules in the interstellar medium. One of the most exciting aspects of the study of Alfven waves is their potential to illuminate the nature of cosmic magnetic fields themselves. Magnetic fields are fundamental to many astrophysical processes, and understanding how these fields evolve is crucial for unraveling the mysteries of the universe. Alfven waves may provide a unique window into the inner workings of these fields, revealing how they are generated, sustained, and amplified. The interplay between Alfven waves and magnetic fields could also shed light on the nature of dark matter and dark energy, two of the most enigmatic components of the universe. In recent years, advances in observational techniques and computational models have made it possible to study Alfven waves with greater precision. New space missions, such as the Parker Solar Probe and the Solar Orbiter, are providing high-resolution data on the Sun's magnetic fields and the behavior of plasma in the solar corona. These missions are offering a wealth of information that can help scientists understand how Alfven waves propagate in different stellar environments. Additionally, more powerful telescopes and space-based instruments are allowing researchers to study the magnetic fields and plasma in distant galaxies, providing new insights into how Alfven waves operate in the broader universe. The role of Alfven waves in the formation and evolution of cosmic structures is another area of intense research. These waves may influence the formation of galactic filaments, the vast, thread-like structures that stretch across the cosmos. These filaments are thought to be composed of dark matter, gas, and dust, and they play a key role in the large-scale structure of the universe. Alfven waves could contribute to the motion of gas within these filaments, affecting the distribution of matter and the formation of galaxies. By studying the interaction between Alfven waves and the material that makes up these filaments, scientists hope to gain a deeper understanding of how galaxies form and evolve over time. The study of Alfven waves also holds promise for advancing our understanding of plasma physics and the behavior of magnetized fluids in general. Plasma, which is the most common state of matter in the universe, is a complex and highly dynamic substance. Understanding how Alfven waves propagate through plasma is key to unlocking many of the mysteries of the universe. Furthermore, these waves have practical applications here on Earth, particularly in the field of fusion energy research. The behavior of Alfven waves in laboratory plasmas can offer insights into how to control and confine plasma for use in nuclear fusion reactors. By mimicking the conditions found in stars, researchers hope to develop clean and sustainable energy sources for the future. The study of Alfven waves is a journey that touches upon nearly every aspect of astrophysics. From their role in the behavior of plasma in stars to their influence on the dynamics of galaxies and the evolution of the universe itself, these magnetic oscillations provide a crucial piece of the puzzle. As we continue to investigate the nature of Alfven waves, we will undoubtedly uncover new insights into the fundamental processes that shape the cosmos. Looking forward, the next steps in this field of research will likely focus on the development of more sophisticated models and observational techniques. With each new discovery, we come closer to understanding the intricate web of magnetic interactions that govern the behavior of matter on both large and small scales. As technology advances and our ability to observe distant regions of space improves, the mysteries of Alfven waves will continue to unfold, offering exciting new opportunities for scientific exploration and discovery. As the study of Alfven waves continues to evolve, the next major frontier lies in how these waves could help explain some of the most mysterious and dynamic aspects of astrophysical phenomena. For instance, one area that has garnered increasing interest is the role of Alfven waves in the acceleration of cosmic rays. Cosmic rays are high-energy particles that travel through space at nearly the speed of light. Their origins remain an ongoing mystery, but some scientists believe that Alfven waves could play a crucial role in their acceleration. Cosmic rays are thought to originate from extreme environments such as supernovae and active galactic nuclei, where the conditions are ideal for the generation of high-energy particles. The energy required to accelerate particles to relativistic speeds is immense, and the mechanism behind this process is still not fully understood. Alfven waves may provide a link between the magnetic fields in these regions and the acceleration of cosmic rays. As these waves propagate through the plasma surrounding such energetic events, they could transfer energy to charged particles, helping them reach the high velocities observed in cosmic rays. By studying how Alfven waves interact with the plasma in these extreme environments, scientists can gain insights into the mechanisms of particle acceleration, which could also have implications for understanding the nature of high-energy astrophysical phenomena like gamma-ray bursts and black hole jets. These insights might also help improve our understanding of the behavior of cosmic rays when they enter our solar system, where they pose a potential threat to space exploration and human-made satellite systems. In addition to cosmic rays, Alfven waves may also be key to understanding the phenomenon of magnetic reconnection. Magnetic reconnection occurs when oppositely directed magnetic fields come into close contact, causing them to reconnect in a new configuration. This process releases enormous amounts of energy and is responsible for a variety of astrophysical phenomena, including solar flares and coronal mass ejections. Alfven waves are thought to play a role in the process of magnetic reconnection by transporting energy to regions where the reconnection occurs. This interaction can help trigger the explosive release of energy that is observed in these events. The study of Alfven waves and magnetic reconnection is vital not just for understanding solar and stellar phenomena but also for improving our predictions of space weather. A better understanding of how Alfven waves interact with the Sun's magnetic fields could allow for more accurate forecasting of solar flares and coronal mass ejections, which can have far-reaching effects on Earth's space environment. These events can disrupt satellite communications, GPS systems, and power grids, so understanding and predicting them is a critical area of research. Another fascinating aspect of Alfven waves is their potential to influence the behavior of plasma in environments beyond our solar system. In particular, researchers are beginning to examine how these waves might play a role in the behavior of intergalactic plasma. The vast expanse between galaxies is not empty. It is filled with a diffuse plasma that interacts with magnetic fields. Alfven waves in this intergalactic plasma could help explain how energy is distributed across large distances in the universe, influencing the structure and evolution of galaxy clusters. By studying Alfven waves in these environments, scientists could gain new insights into the overall dynamics of the universe and the processes that govern its evolution. As we venture into even more distant parts of the universe, Alfven waves may provide crucial information about the nature of dark matter and dark energy. Both of these mysterious components make up most of the universe's mass energy content, yet their properties remain elusive. Some theorists have speculated that Alfven waves could interact with dark matter or dark energy in ways that we have not yet fully understood. If Alfven waves play a role in the behavior of dark matter, they could provide a means of detecting and studying this invisible substance. Similarly, if dark energy influences the behavior of magnetic fields and plasma, Alfven waves could serve as a tool for exploring the nature of this mysterious force. While the direct observation of Alfven waves in distant galaxies or across vast cosmic distances remains a challenge, advances in technology are making it increasingly possible to study these waves in greater detail. Upcoming space missions, such as the James Webb Space Telescope and the upcoming missions focused on studying the magnetic fields of distant stars and galaxies, may allow scientists to indirectly detect the effects of Alfven waves in the plasma surrounding these objects. These observations will likely provide new data that will enhance our understanding of how Alfven waves operate in different astrophysical environments. The study of Alfven waves also has implications for our understanding of the fundamental nature of plasma and magnetohydrodynamics, MHD, the branch of physics that deals with the behavior of magnetized fluids. Alfven waves are a key feature of MHD, and their study offers important insights into how plasma responds to magnetic fields. This research could have practical applications beyond astrophysics, especially in the field of fusion energy. In fusion reactors, plasma is confined using magnetic fields, and understanding how Alfven waves behave in these environments could improve our ability to control and manipulate plasma for energy production. One area where this knowledge could have significant impact is in the development of tokamaks, the donut-shaped reactors used in fusion experiments. These reactors use powerful magnetic fields to confine plasma at extremely high temperatures, mimicking the conditions found in stars. However, the plasma in these reactors is highly dynamic, and controlling its behavior is one of the biggest challenges in fusion research. Alfven waves can interact with plasma in ways that might help or hinder efforts to stabilize it. By studying how these waves affect plasma in fusion reactors, scientists may be able to develop better techniques for controlling and confining plasma, bringing us one step closer to achieving sustainable fusion energy. Alfven waves are an essential part of the cosmic puzzle, influencing everything from solar activity to the behavior of intergalactic plasma. Their role in the transfer of energy, acceleration of particles, and magnetic interactions makes them a key player in many astrophysical processes. As we continue to investigate the properties of these waves and their impact on the universe, we will undoubtedly uncover new and exciting insights into the behavior of plasma, magnetic fields, and the very nature of the universe itself. The study of Alfven waves is not just a field of academic interest, it is a crucial avenue of research that promises to deepen our understanding of the cosmos and unlock the mysteries of the universe. As the exploration of Alfven waves continues, the implications for both astrophysics and other fields of science become ever more apparent. For example, one of the key features of Alfven waves is their ability to transport energy across vast distances without significant loss. This ability makes them a vital player in the study of large-scale cosmic processes. In stellar environments, such as the outer layers of stars, Alfven waves can help explain the dynamics of magnetic fields and the transfer of energy from a star's interior to its outer atmosphere. In particular, the behavior of Alfven waves in stellar coronae, the outermost layer of a star's atmosphere, remains a subject of active research. The corona of the Sun, for instance, is millions of degrees hotter than its surface, a phenomenon that has puzzled scientists for years. How does such a stark temperature difference arise? One proposed explanation is that Alfven waves, created by magnetic interactions deep within the Sun, may travel outward to the corona, where they dissipate their energy, heating the plasma to extreme temperatures. This process could help explain why the Sun's corona is hotter than its surface and why it exhibits such complex, dynamic behavior. Researchers are also keenly interested in the role that Alfven waves play in the solar wind, the continuous stream of charged particles that emanate from the Sun and extends throughout the solar system. The solar wind interacts with Earth's magnetosphere, creating phenomena such as the aurora borealis and geomagnetic storms. Alfven waves are thought to be instrumental in shaping the properties of the solar wind, particularly in terms of how it interacts with the magnetic fields of planets and other objects in the solar system. Understanding how these waves affect the solar wind could lead to more accurate models of space weather and improve our ability to predict and protect against solar storms that impact Earth. Beyond the confines of our own solar system, Alfven waves may offer valuable insights into the broader behavior of interstellar plasma. The interstellar medium, which is composed of gas and dust particles scattered between stars, is also magnetized. As magnetic fields travel through this medium, Alfven waves propagate along them, carrying energy across vast stretches of space. By studying these waves, astronomers hope to gain a better understanding of the structure and evolution of galaxies. For example, Alfven waves may be involved in the processes that govern the formation of stars, helping to regulate the flow of material and energy in molecular clouds, the birthplaces of new stars. In galaxy clusters, where magnetic fields and plasma are widespread, Alfven waves may help explain the distribution of energy and the dynamics of these large cosmic systems. The study of these waves in clusters could lead to insights into the large-scale processes that shape the universe, such as the formation of galactic structures, the evolution of galaxies, and the impact of dark matter on these processes. Given the profound importance of these waves in galactic dynamics, the ability to observe them directly could revolutionize our understanding of how galaxies evolve over time. One of the most exciting possibilities that arises from the study of Alfven waves is their potential to contribute to the growing body of research on gravitational waves. Gravitational waves, first predicted by Einstein and later detected by LIGO, are ripples in spacetime caused by the acceleration of massive objects. While gravitational waves are typically associated with catastrophic events like black hole mergers, researchers have also speculated that Alfven waves could play a role in gravitational wave generation under certain conditions. This connection, if confirmed, could open up new avenues for the study of cosmic phenomena and add another layer of complexity to our understanding of spacetime. The role of Alfven waves in particle acceleration has already been mentioned, but it is worth emphasizing how significant this process is. In astrophysical contexts, the acceleration of particles to relativistic speeds can release enormous amounts of energy, which in turn can influence the behavior of entire stellar systems or even entire galaxies. As charged particles are accelerated by Alfven waves, they can become energetic enough to be ejected from their host stars or galaxies, contributing to the interstellar or intergalactic medium. The study of these particle acceleration mechanisms can shed light on the processes that fuel the energetic phenomena observed in high-energy astrophysics, such as supernovae, gamma-ray bursts, and active galactic nuclei. In more practical terms, the study of Alfven waves is also deeply relevant to the field of space exploration. Space agencies like NASA and the European Space Agency, ESA, rely on accurate models of plasma behavior in space to ensure the safety of their spacecraft. The interaction of Alfven waves with spacecraft, for instance, can cause changes in the spacecraft's trajectory or affect the functionality of its instruments. Understanding the effects of Alfven waves on spacecraft could improve mission planning and ensure that spacecraft are able to safely navigate through environments like the magnetospheres of planets or the solar wind. The study of Alfven waves also has profound implications for the future of fusion energy research. As fusion reactors aim to replicate the processes that occur in stars, the control of plasma is paramount. Alfven waves, due to their interaction with charged particles in plasma, are a key consideration for researchers working to achieve sustainable nuclear fusion. If researchers can better understand the dynamics of Alfven waves in fusion reactors, they may be able to develop better methods for controlling plasma behavior, potentially paving the way for more efficient and reliable fusion energy production in the future. Another fascinating area where Alfven waves are making a difference is in the study of high-energy astrophysical phenomena, such as magnetars. Magnetars are neutron stars with incredibly strong magnetic fields, far stronger than those found in typical stars or even regular neutron stars. These intense magnetic fields create unique conditions for the propagation of Alfven waves. The study of Alfven waves and magnetars could provide critical information about the nature of extreme magnetic fields and the behavior of matter under such conditions. The energy released by Alfven waves in such environments could help explain the mysterious bursts of high-energy radiation observed from magnetars. Looking to the future, researchers are exploring new methods for detecting and observing Alfven waves across vast cosmic distances. While it is challenging to directly observe these waves, their presence can be inferred through their effects on nearby plasma. The development of new observational techniques and instruments, such as advanced radio telescopes and space-based observatories, could provide more detailed measurements of Alfven waves in distant stars, galaxies, and other astrophysical environments. These advancements in observational technology will help scientists create more accurate models of Alfven wave behavior, deepening our understanding of the universe. Alfven waves are a central feature of the cosmos, influencing everything from stellar behavior to the dynamics of galaxies and intergalactic space. Their role in particle acceleration, magnetic field interactions, and energy transfer makes them a critical component of many astrophysical processes. As researchers continue to unravel the mysteries of these waves, we will undoubtedly gain new insights into the workings of the universe, from the smallest scales to the largest cosmic structures. The study of Alfven waves is not just an academic pursuit, it is a gateway to understanding the fundamental forces that govern the behavior of plasma, magnetic fields, and energy across the universe. As we continue to explore the intricate relationship between Alfven waves and astrophysical phenomena, it's crucial to delve deeper into the theoretical frameworks that underpin these waves. Alfven waves are not merely a curiosity but a profound aspect of plasma physics that has far-reaching implications in both theoretical and observational cosmology. To understand these waves, we must first consider the nature of plasma itself and how Alfven waves arise in such environments. Plasma, which is often referred to as the fourth state of matter, is a highly conductive mixture of ions and free electrons. It can exist in a variety of conditions, such as in the interstellar medium, stellar interiors, and even in the artificial environments created in fusion reactors. Plasma is also where magnetic fields and electric currents interact in unique ways. Alfven waves emerge when these magnetic fields oscillate through plasma, creating disturbances that propagate outward in the form of waves. These waves are specifically tied to the properties of the magnetic fields themselves and the plasma's ability to conduct electricity. To better understand how Alfven waves interact with plasma, consider the behavior of magnetic fields in various astrophysical environments. In stellar coronae, for example, magnetic fields are believed to be twisted and tangled due to the complex movement of plasma. This magnetic turbulence is thought to be responsible for generating Alfven waves. When these waves propagate through the corona, they carry energy that can heat the plasma to extreme temperatures, potentially explaining the high-energy processes observed in stars. The relationship between Alfven waves and plasma density is another critical aspect to consider. Plasma density, which refers to the number of particles per unit volume, significantly affects the propagation speed and characteristics of Alfven waves. In regions of high-density plasma, the waves travel more slowly, whereas in lower-density regions, they can propagate more rapidly. This density dependence is essential for understanding the various regions of stars and the solar wind, where plasma density fluctuates. As Alfven waves move through regions with varying densities, their behavior can shift, affecting their ability to transfer energy and heat to surrounding plasma. The ability of Alfven waves to interact with plasma is not just limited to stellar environments. In the vast expanse of intergalactic space, plasma is sparse and turbulent. Even in these regions, Alfven waves play a role in shaping the behavior of cosmic magnetic fields. One of the ways in which Alfven waves interact with intergalactic plasma is by transporting energy across vast distances. This energy transfer process helps to maintain the magnetic fields that exist in galaxies, as well as the larger structures that exist between galaxies. Without the action of Alfven waves, these magnetic fields would likely become weaker, leading to a collapse of many cosmic structures over time. In recent years, scientists have also been studying the role of Alfven waves in galactic jets. These jets, which are streams of plasma ejected from the centers of galaxies, are among the most energetic and spectacular phenomena in the universe. The magnetic fields at the heart of these jets are thought to be heavily influenced by Alfven waves, which could play a role in the acceleration of particles within the jets. Understanding how these waves interact with the plasma in these jets is key to unlocking the mysteries of high-energy astrophysical processes. Another fascinating area of research involves the role of Alfven waves in the acceleration of cosmic rays. Cosmic rays, high-energy particles that travel through space, are thought to be produced in a variety of astrophysical environments, such as supernovae, active galactic nuclei, and black hole accretion disks. Alfven waves are believed to be one of the key mechanisms by which these cosmic rays are accelerated to such high energies. By interacting with Alfven waves, charged particles are able to gain energy and become accelerated to speeds approaching the speed of light. This process is crucial for understanding the origins of cosmic rays and their behavior as they travel through space. As we consider the broader implications of Alfven waves, it's clear that they are essential to the understanding of numerous astrophysical phenomena, both large and small. Their presence in stellar atmospheres, interstellar media, and even galaxy clusters suggests that they are a universal feature of plasma environments. The challenge for scientists is to unravel the precise mechanisms by which these waves affect the behavior of plasma, magnetic fields, and energy transfer in various astrophysical systems. Recent advancements in observational technology are helping to bring Alfven waves into sharper focus. Observatories that specialize in the study of magnetic fields and plasma behavior, such as the Parker Solar Probe and the Solar and Heliospheric Observatory, SOHO, have begun to collect data that could reveal new insights into the propagation of Alfven waves in the solar system. With these tools, scientists are now able to observe the interactions between Alfven waves and the Sun's corona in real time, providing unprecedented opportunities for study. The role of Alfven waves in space weather also cannot be understated. Space weather, which refers to the conditions in space that affect Earth's magnetic field and atmosphere, is heavily influenced by the solar wind and its interactions with the planet's magnetosphere. The solar wind, a continuous stream of charged particles from the Sun, is filled with Alfven waves, which can cause fluctuations in the magnetic field around Earth. These fluctuations can lead to geomagnetic storms, which can disrupt communication systems, navigation, and even power grids. Understanding the behavior of Alfven waves in the solar wind is critical for predicting and mitigating the effects of space weather on Earth. Beyond the confines of our solar system, Alfven waves are also believed to play a role in the behavior of plasma in the interstellar medium. The interstellar medium, composed of gas and dust particles that fill the spaces between stars, is magnetized, creating the ideal conditions for Alfven waves to propagate. As these waves travel through the medium, they can influence the distribution of energy and matter in galaxies. For instance, Alfven waves are thought to be involved in the process of star formation, as they can help regulate the flow of material and molecular clouds, the regions where new stars are born. By studying how Alfven waves interact with these clouds, astronomers hope to gain a better understanding of the conditions that lead to the birth of stars and planets. As we explore further, we also see the potential of Alfven waves to contribute to the study of dark matter and dark energy. Although these elusive phenomena remain largely unexplained, some researchers have speculated that Alfven waves could play a role in their detection. Dark matter, which is thought to account for much of the universe's mass, and dark energy, which is believed to be responsible for the accelerated expansion of the universe, are both highly mysterious. The study of Alfven waves in the context of these phenomena could provide valuable clues about their nature and the forces that govern their behavior. To fully appreciate the importance of Alfven waves, we must also consider their connection to other wave phenomena in plasma physics. For example, in addition to Alfven waves, there are other types of waves, such as sound waves and magnetoacoustic waves, that also interact with plasma and magnetic fields. These waves share some similarities with Alfven waves but differ in how they propagate and interact with plasma. By studying the differences and similarities between these various types of waves, researchers can develop more comprehensive models of plasma behavior, further enhancing our understanding of the universe. The study of Alfven waves is an essential part of modern astrophysics. These magnetic oscillations, which govern the behavior of plasma in stars, galaxies, and interstellar space, have profound implications for our understanding of cosmic phenomena. From their role in star formation to their contribution to the acceleration of cosmic rays and their potential to reveal new insights into dark matter, Alfven waves are an indispensable part of the cosmic puzzle. As our observational tools improve and our theoretical models evolve, we can expect to learn even more about these fascinating waves and their impact on the universe. Alfven waves are not only a crucial component of plasma physics, but their study extends to understanding the broader dynamics of cosmic structures. The role of these waves in the evolution of galaxies, the behavior of supernova remnants, and the dynamics of black holes and their accretion disks offers insights into processes that shape the universe over vast timescales. In the case of supernova remnants, the powerful explosion of a star releases enormous amounts of energy, creating shock waves that propagate through the surrounding interstellar medium. These shock waves can interact with Alfven waves, which in turn influence the magnetic fields present in the remnants. The interplay between shock waves and Alfven waves is a subject of significant interest, as it may explain the observed behavior of certain cosmic phenomena. For instance, it is believed that Alfven waves could contribute to the acceleration of particles in supernova remnants, providing one potential mechanism for the production of cosmic rays. Understanding how these waves interact with the plasma in these environments could shed light on the processes that govern the evolution of stars and galaxies. The study of Alfven waves is also important in the context of black holes and the magnetic field surrounding them. In the regions near the event horizon of a black hole, plasma is heated to extreme temperatures, and magnetic fields can become twisted and amplified. Alfven waves, which are tightly linked to these magnetic fields, may play a significant role in the dynamics of the accretion disk, the swirling disk of gas and dust that orbits a black hole before being drawn into it. The interaction between Alfven waves and the plasma in the accretion disk could influence the rate at which material falls into the black hole, potentially affecting the growth and behavior of the black hole itself. In addition to these astrophysical phenomena, Alfven waves are also crucial in the study of plasma confinement in fusion reactors. Fusion, the process that powers stars, involves the merging of light atomic nuclei at high temperatures and pressures. Replicating this process on Earth for clean energy generation requires the containment of high-temperature plasma in reactors. The behavior of Alfven waves in these environments can help scientists understand how to control and stabilize plasma, preventing it from escaping the magnetic confinement fields. This understanding is key to the development of fusion energy as a viable source of power in the future. The role of Alfven waves in space weather, which we touched on earlier, cannot be overstated. The Sun's magnetic activity directly impacts Earth's magnetosphere, and Alfven waves play a significant part in these interactions. The solar wind, filled with charged particles and magnetic fields, is a source of much of the space weather that can affect our planet. Alfven waves within the solar wind can lead to disturbances in Earth's magnetic field, causing geomagnetic storms that can disrupt satellite communications, GPS systems, and power grids. By studying how these waves interact with the solar wind, scientists hope to predict and mitigate the effects of space weather, providing better protection for our technological infrastructure. The link between Alfven waves and plasma turbulence is another area of significant interest. Plasma turbulence refers to the chaotic, irregular motion of plasma particles, which occurs when plasma becomes unstable due to interactions between magnetic fields and electric currents. This turbulence can lead to the formation of various types of waves, including Alfven waves. Understanding the role of Alfven waves in plasma turbulence is important for a range of applications, from astrophysics to fusion energy research. Plasma turbulence plays a key role in the transport of energy and particles within stars and galaxies, influencing their behavior over time. By studying how Alfven waves contribute to this turbulence, researchers can develop more accurate models of plasma behavior in various environments. An intriguing aspect of Alfven waves lies in their potential to be used as a tool for probing the properties of plasma in distant cosmic objects. Observations of Alfven waves can provide valuable information about the magnetic fields, densities, and temperatures of distant regions, such as the interiors of stars or the space around black holes. This type of observational technique is especially important given the difficulty of directly observing many astrophysical phenomena. For example, the magnetic fields in the corona of the Sun cannot be directly observed, but by studying the Alfven waves that propagate through this region, scientists can infer the properties of the magnetic field and its role in solar activity. A key challenge in the study of Alfven waves is the difficulty of simulating these waves accurately in laboratory conditions. While we have gained a significant amount of knowledge about Alfven waves through observations and mathematical modeling, recreating the precise conditions of plasma and magnetic fields that allow these waves to form is no small feat. Advances in computational modeling and experimental techniques are helping to bridge this gap, allowing scientists to simulate the behavior of Alfven waves in increasingly realistic environments. These advancements are critical for enhancing our understanding of Alfven waves and their role in various cosmic phenomena. As we explore the potential of Alfven waves further, we must also consider their implications for the broader field of plasma physics. Plasma physics, which deals with the behavior of ionized gases and their interactions with magnetic fields, is a rapidly evolving field with numerous applications across various scientific disciplines. From understanding the fundamental processes that govern the behavior of matter in extreme environments to developing new technologies for energy production and space exploration, the study of Alfven waves is central to advancing our knowledge of plasma dynamics. One of the most exciting frontiers in Alfven wave research is the possibility of discovering new forms of plasma behavior that have never been observed before. While Alfven waves are well established in many plasma environments, there are still many unknowns regarding how these waves interact with different types of plasma. For example, in dense environments such as the interiors of stars, it is possible that Alfven waves may exhibit behavior that differs from what we observe in more diffuse plasmas. Additionally, in regions of high turbulence or extreme magnetic fields, the interactions between Alfven waves and plasma could lead to the formation of entirely new wave phenomena. As observational techniques improve and our theoretical models become more sophisticated, the potential for discovering new and unexpected plasma behaviors grows. In the context of space exploration, Alfven waves may also play a crucial role in the behavior of plasma in spacecraft and space missions. For example, spacecraft traveling through the solar wind may encounter Alfven waves that influence their movement and behavior. Understanding how these waves affect spacecraft could be vital for the design of future space missions, especially those targeting distant regions of the solar system or interstellar space. By incorporating the study of Alfven waves into mission planning, scientists can ensure that spacecraft are better equipped to handle the challenges posed by the complex plasma environments they will encounter. The study of Alfven waves is not only an exciting field of research but one that is deeply intertwined with our understanding of the universe itself. From the fundamental processes that drive the formation and evolution of cosmic structures to the practical applications that could benefit humanity, the study of these waves offers a glimpse into some of the most profound mysteries of the cosmos. As we continue to push the boundaries of what we know about plasma physics, magnetic fields, and the behavior of matter in extreme environments, Alfven waves will undoubtedly remain a key focus of scientific inquiry. Alfven waves are a central component of plasma physics and play a vital role in many astrophysical processes. From their influence on star formation and black hole dynamics to their potential to reveal the mysteries of dark matter, these waves are a crucial aspect of our understanding of the universe. As technology and research methods continue to advance, our knowledge of Alfven waves will undoubtedly deepen, providing new insights into the behavior of plasma and magnetic fields in a variety of environments. Whether we are studying the solar wind, exploring the interiors of stars, or seeking to harness fusion energy on Earth, Alfven waves will continue to shape our understanding of the cosmos for years to come. As we continue to explore the mysteries surrounding Alfven waves, it's important to recognize that they represent one of the most fascinating and dynamic aspects of plasma physics. As we journey deeper into the intricate behavior of these waves, we start to see how essential they are not just for understanding the natural forces that shape our universe, but for the technological advances that could one day revolutionize human exploration and energy production. While Alfven waves have traditionally been associated with astrophysical phenomena like stars and black holes, the implications of their behavior extend far beyond the cosmic scale. Scientists are beginning to understand how these waves could help us solve some of the most pressing challenges in space exploration, such as protecting spacecraft from dangerous solar winds or even manipulating plasma for advanced propulsion systems. By harnessing the power of Alfven waves, humanity could unlock new ways to explore the farthest reaches of the galaxy, potentially paving the way for interstellar travel. One of the key areas where Alfven waves are showing promise is in the field of magnetized plasma propulsion. The idea behind this technology is to use the behavior of plasma in magnetic fields to accelerate spacecraft to extreme speeds. The manipulation of Alfven waves could play a significant role in this process by offering a new method for controlling the plasma, making it more efficient and allowing for faster travel through space. In essence, Alfven waves could become a crucial tool in the development of faster, more efficient spacecraft, reducing the travel time between distant planets, or even between stars. The ability to use Alfven waves for space propulsion could also have implications for the development of fusion energy. If scientists can better understand and control Alfven waves within fusion reactors, they could increase the efficiency of energy generation and make fusion a more viable source of clean, sustainable power. This connection between Alfven waves and fusion technology demonstrates how closely tied the study of cosmic phenomena is to the challenges we face here on Earth. It's a perfect example of how breakthroughs in understanding the universe can lead to innovations that directly benefit humanity. As we think about the long-term future of space exploration, it's also worth considering the role that Alfven waves could play in the study of other star systems. While we currently rely on telescopes and other instruments to gather data about distant stars and planets, the future could hold new methods of probing these environments, including the use of Alfven waves. By studying the way these waves propagate through the plasma surrounding stars, scientists may be able to gain deeper insights into the composition, behavior, and evolution of distant systems, all without the need for direct observation. This could open up new avenues of exploration and discovery, bringing us closer to understanding the vast and mysterious universe we live in. Another area where Alfven waves could have significant applications is in the study of the solar system's outer reaches. The farthest edges of our solar system, beyond the orbit of Neptune, are still largely unexplored, and many questions remain about the behavior of plasma in this distant region. As spacecraft venture further out, they will inevitably encounter Alfven waves within the solar wind, and studying how these waves behave in such a remote environment could reveal valuable information about the dynamics of the outer solar system. Moreover, understanding the role of Alfven waves in these regions could help scientists better predict how cosmic phenomena like solar flares and coronal mass ejections might affect our planet, or any future space missions that venture into deep space. While these potential applications of Alfven waves are exciting, they are still in the early stages of research. Scientists are continuing to refine their understanding of how these waves behave in different environments, and how they can be controlled and utilized. However, as we move forward in this field, it is likely that Alfven waves will become a key part of the toolkit for scientists and engineers working on the frontier of space exploration and energy production. In addition to their practical applications, Alfven waves also provide a unique opportunity to probe the fundamental nature of plasma itself. Plasma, the fourth state of matter, is vastly different from the solids, liquids, and gases we are familiar with. Understanding how plasma behaves in the presence of magnetic fields, particularly through the lens of Alfven waves, is crucial for advancing our knowledge of the universe. The study of these waves offers a window into the intricate interactions between charged particles, magnetic fields, and energy that govern the behavior of matter on both cosmic and microscopic scales. Furthermore, as we explore the interactions between Alfven waves and various plasma phenomena, we uncover the complex ways in which energy is transported throughout the universe. From the energy that powers stars to the way that cosmic radiation propagates through space, Alfven waves play an integral role in shaping the dynamics of the cosmos. Understanding these waves is therefore not just about studying the behavior of plasma in isolation, but about uncovering the broader forces that govern the evolution of the universe itself. The role of Alfven waves in the solar system, and their connection to the space weather that affects Earth, is an area that is rapidly gaining attention. Space weather, driven by the sun's activity, can have significant impacts on satellite communications, navigation systems, and even power grids on Earth. By studying Alfven waves in the solar wind, scientists hope to develop better models of space weather and improve our ability to predict and mitigate the effects of solar storms. This research is crucial for the ongoing advancement of space-based technologies and for ensuring the safety of the systems we rely on here on Earth. As we delve deeper into the mysteries of Alfven waves, it's clear that they are not just fascinating phenomena confined to the study of plasma physics. They represent a bridge between the cosmic forces that shape the universe and the technological challenges we face here on Earth. Whether we are studying the behavior of stars, exploring the depths of space, or working to harness the power of fusion energy, Alfven waves are a crucial piece of the puzzle that could unlock new frontiers in science and technology. In the coming years, as our understanding of Alfven waves continues to evolve, we can expect to see even more groundbreaking discoveries and innovations. These waves are not only a tool for understanding the universe, they are a key to unlocking its mysteries. By continuing to study and harness the power of Alfven waves, we are taking a step closer to understanding the fundamental forces that govern the cosmos and finding new ways to use that knowledge to improve our lives. Alfven waves are an integral part of plasma physics and astrophysics, with far-reaching implications for space exploration, energy production, and our understanding of the universe. From their role in the behavior of plasma around stars and black holes to their potential applications in fusion energy and spacecraft propulsion, these waves offer a unique and powerful lens through which we can explore the cosmos. As research continues to advance, we are only beginning to scratch the surface of what these waves can teach us about the universe and how we can use that knowledge to drive technological progress and scientific discovery. The study of Alfven waves is not just about understanding a specific phenomenon, it's about unlocking the secrets of the universe itself. As we continue our exploration of Alfven waves, it's essential to consider the remarkable implications they hold for understanding the very structure of the universe. These waves are not just simple disturbances in plasma, they are key players in the interplay of magnetic fields, charged particles, and energy transfer across vast cosmic distances. By diving deeper into the intricate mechanisms that govern these waves, we can begin to appreciate the larger patterns that shape the cosmos. One of the fundamental mysteries that Alfven waves help us address is the behavior of magnetic fields in the universe. We often take magnetic fields for granted here on Earth, where they are used in everything from electronics to navigation. But in the vast expanse of space, magnetic fields take on an entirely different role. They shape the behavior of plasma, guide the movement of charged particles, and even influence the very formation of stars and galaxies. The study of Alfven waves gives us critical insight into how these magnetic fields interact with plasma. These waves are essentially the sound of plasma, vibrating at the frequency of the magnetic field. Just as sound waves in the air carry energy through vibrations, Alfven waves carry magnetic energy through the plasma. This means that understanding the movement of Alfven waves allows scientists to trace the flow of energy throughout the cosmos. This is especially important when it comes to understanding phenomena like the solar wind, the auroras, and even the behavior of plasma in distant galaxies. The impact of Alfven waves extends far beyond our understanding of cosmic phenomena. In recent years, research has begun to show that these waves may also play a significant role in maintaining the stability of various plasma environments, including those found in the Earth's magnetosphere. The magnetosphere is the region of space controlled by Earth's magnetic field, which acts as a protective shield against harmful solar radiation. Alfven waves help maintain the balance of energy in this environment, ensuring that the plasma remains in a stable state and preventing disruptions that could cause damage to satellites, power grids, and communication systems. Understanding how Alfven waves contribute to the stability of the magnetosphere is crucial for predicting and mitigating the effects of space weather events, such as geomagnetic storms. These storms are caused by disturbances in the solar wind that can interact with Earth's magnetic field, leading to the release of energy in the form of charged particles. Alfven waves play a key role in this process, helping to regulate the flow of energy and ensuring that it is dissipated in a controlled manner. Without this mechanism, space weather events could be far more disruptive, potentially causing widespread damage to our technological infrastructure. This knowledge of how Alfven waves affect Earth's magnetosphere also opens up new avenues of research into the potential for protecting future space missions from harmful radiation. As humanity ventures further into space, spacecraft will inevitably encounter intense radiation from the Sun and other cosmic sources. By understanding how Alfven waves work to regulate plasma and magnetic fields, we can develop new technologies that protect astronauts and spacecraft from these dangers. This could include the development of magnetic shields that mimic the protective effects of Earth's magnetosphere, offering a safer environment for space exploration. The applications of Alfven waves are not limited to protecting spacecraft and satellites. These waves also offer a unique opportunity to study the physics of other celestial bodies, such as the gas giants and their moons. Planets like Jupiter, Saturn, and Neptune all have strong magnetic fields and complex plasma environments that could be influenced by Alfven waves. By studying how these waves propagate through the plasma surrounding these planets, scientists can gain valuable insights into the composition and behavior of their atmospheres, magnetic fields, and moons. One of the most intriguing aspects of Alfven waves is their potential connection to other phenomena in space, such as cosmic rays and the behavior of supermassive black holes. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, and they are thought to play a significant role in the processes that govern the formation of galaxies and stars. Understanding how Alfven waves interact with these particles could provide crucial information about how energy is transferred across the universe and how cosmic structures evolve over time. Similarly, Alfven waves may play a role in the behavior of supermassive black holes, which are believed to exist at the centers of most galaxies. These black holes generate intense magnetic fields that influence the movement of plasma and the surrounding material. By studying the behavior of Alfven waves in these environments, scientists hope to learn more about the nature of these mysterious objects and the forces that govern their interactions with the rest of the galaxy. At a more practical level, the study of Alfven waves is also critical for the advancement of fusion energy. As we mentioned earlier, Alfven waves are integral to the behavior of plasma in fusion reactors. In these reactors, the goal is to replicate the processes that occur in the core of stars, where plasma is heated to extremely high temperatures and pressure to produce energy. However, maintaining control over the plasma in a fusion reactor is a major challenge, as the plasma is highly unstable and prone to disruptions. By understanding how Alfven waves interact with the plasma in these reactors, scientists can develop better ways to control and stabilize the plasma, improving the efficiency of fusion reactions. This could be a game changer for energy production, offering a clean, sustainable source of power that could help address the growing energy needs of the world. In this sense, Alfven waves are not just a tool for understanding the cosmos, they are a crucial part of our efforts to solve some of the most pressing challenges facing humanity today. As we look to the future, the study of Alfven waves will undoubtedly continue to reveal new mysteries and insights about the universe. With each new discovery, we are uncovering more about the intricate relationships between magnetic fields, plasma, and energy in space. These waves are not just a fascinating aspect of plasma physics, they are a window into the very forces that shape the cosmos. The potential for new discoveries is vast, and as technology advances, we may find even more applications for our understanding of Alfven waves. For example, researchers are already exploring the possibility of using these waves in space propulsion systems, where the manipulation of plasma could provide a new method for moving spacecraft at higher speeds. In the long term, this could open up entirely new frontiers for space exploration, allowing humanity to travel further into the cosmos than ever before. Similarly, As we continue to study Alfven waves and their role in the behavior of plasma, we may uncover new ways to harness their energy for use here on Earth. While we are still a long way from fully understanding the potential of these waves, the possibilities are tantalizing. From improved energy generation to better space weather prediction and protection, the study of Alfven waves holds the promise of revolutionizing both our understanding of the universe and our ability to navigate it. Alfven waves represent one of the most fascinating and powerful phenomena in the universe. These waves are central to our understanding of plasma behavior, magnetic fields, and energy transfer, not only in space but also in applications like fusion energy and space exploration. As we continue to study these waves, we are uncovering new layers of knowledge that could shape the future of science and technology. With each breakthrough, we move closer to unlocking the mysteries of the cosmos and harnessing the power of the universe for the benefit of humanity. As we continue to explore the immense significance of Alfven waves, we must dive even deeper into their role in shaping the dynamics of our solar system and beyond. While we've touched on their importance in maintaining the stability of Earth's magnetosphere, the study of these magnetic oscillations goes far beyond our planet. Alfven waves play an essential part in the behavior of stars, the movement of plasma in the solar wind, and the interactions between celestial bodies within the vast reaches of interstellar space. One area where Alfven waves reveal their influence is in the solar corona, the outermost layer of the Sun's atmosphere. The Sun is a giant ball of superheated plasma, and the corona, which is much hotter than the surface, has long been one of the Sun's greatest mysteries. Despite its extreme temperature, which can reach millions of degrees, the corona is still not fully understood. Scientists have long struggled to explain how the Sun's energy is transferred from its core to its outer layers. The key to understanding this phenomenon lies in the behavior of Alfven waves. Alfven waves in the solar corona serve as an essential mechanism for transferring energy from the Sun's interior to its outer layers. These waves are generated by the motion of charged particles in the plasma, and their oscillations create waves in the magnetic field lines. These waves propagate outward from the Sun, carrying energy with them. This energy is what contributes to the heating of the corona and the solar wind, which in turn affects space weather and has a direct impact on the conditions in space surrounding Earth. Through studying Alfven waves in the solar corona, researchers have uncovered key insights into the solar wind, which is a continuous stream of charged particles emitted by the Sun. These particles, composed mostly of electrons and protons, travel through space at high speeds and can influence the environments of planets, moons, and even spacecraft. Understanding how Alfven waves affect the solar wind is crucial for predicting space weather events, such as coronal mass ejections, CMEs, and solar flares, that can disrupt communication systems, satellite operations, and power grids on Earth. Alfven waves also help us explain the complex interactions between solar radiation and planetary magnetospheres. As the solar wind flows through space, it encounters the magnetic fields of planets, including Earth. When Alfven waves propagate through the plasma surrounding these planets, they influence the movement of charged particles, leading to phenomena like auroras, those colorful displays of light we see at the poles. These interactions also have broader implications for understanding the long-term stability of planetary environments. In particular, researchers are studying how Alfven waves may influence the habitability of exoplanets located in distant star systems. The study of Alfven waves is not limited to our own solar system, however. These waves provide a unique window into the dynamics of other star systems, galaxies, and the interstellar medium, the vast, empty space between stars. By observing how Alfven waves propagate through different regions of space, astronomers can gain a better understanding of the magnetic fields, plasma, and charged particles that exist in distant parts of the universe. For example, Alfven waves are thought to play a role in the formation and evolution of galaxies, helping to transfer energy and regulate the distribution of matter throughout these vast cosmic structures. As we push further into the realm of interstellar exploration, the ability to detect and analyze Alfven waves in other star systems and galaxies becomes increasingly important. Understanding how these waves behave in different environments can reveal a great deal about the underlying physical processes that govern the formation and evolution of stars and galaxies. This knowledge could also inform the search for life beyond Earth, as it may provide clues about the conditions necessary for the development of habitable planets. In addition to their importance in astrophysical research, Alfven waves are also playing a critical role in cutting-edge fusion research here on Earth. As we've mentioned previously, Alfven waves help us understand how plasma behaves in fusion reactors. But this relationship goes even deeper. In fusion experiments, scientists aim to replicate the processes that occur in the core of stars, where hydrogen nuclei fuse together to form helium and release vast amounts of energy. This process occurs at incredibly high temperatures and pressures, and maintaining the stability of the plasma is one of the most challenging aspects of fusion research. Alfven waves are key to understanding the behavior of plasma in these extreme conditions. They help scientists study how magnetic fields interact with plasma, which is essential for keeping the hot, charged particles contained in the reactor. By manipulating Alfven waves in controlled environments, researchers can stabilize the plasma, reducing the risk of disruptions that could cause the fusion reaction to fail. This ability to control Alfven waves in fusion reactors holds the potential to unlock the door to clean, sustainable energy production, an achievement that could revolutionize the way we generate power and address the global energy crisis. Furthermore, understanding Alfven waves could lead to advances in other areas of plasma physics, such as plasma propulsion systems for space exploration. Plasma propulsion is an exciting area of research that could provide an efficient and sustainable method of space travel. By manipulating plasma using magnetic fields, spacecraft could theoretically achieve high speeds and travel vast distances in a fraction of the time it would take using traditional rocket propulsion systems. Alfven waves play a crucial role in these systems, helping to stabilize the plasma and ensure the efficient transfer of energy. If scientists can master the behavior of these waves, they could pave the way for a new era of space exploration, allowing humanity to venture deeper into the cosmos than ever before. The study of Alfven waves also offers profound insights into the nature of the universe itself. At the most fundamental level, these waves are a manifestation of the interplay between magnetic fields and plasma, two of the most common and powerful forces in the cosmos. By studying the behavior of Alfven waves, we are essentially exploring the fabric of space itself, gaining a deeper understanding of how energy and matter interact on the most basic level. This knowledge could lead to breakthroughs not only in astrophysics and fusion energy but also in other fields of science and technology. Alfven waves are far more than just a scientific curiosity. These magnetic oscillations are essential to understanding the behavior of plasma in a wide range of environments, from the sun's corona to distant galaxies and fusion reactors. They play a crucial role in shaping the magnetic fields that govern the movement of charged particles, transferring energy across vast distances and influencing the very structure of the universe. As our understanding of Alfven waves continues to grow, we are uncovering new insights into the dynamics of the cosmos, opening up exciting possibilities for future research, space exploration, and energy production. The journey to fully comprehend the mysteries of Alfven waves is far from over, and as technology advances, we will undoubtedly discover even more about their significance in the universe. The study of these waves is not just a quest for knowledge, it is a journey toward unlocking the fundamental forces that shape the universe, a journey that will continue to inspire and challenge scientists for generations to come. Continuing the exploration of Alfven waves, it becomes clear that their study not only holds the key to unlocking mysteries of the cosmos but also serves as a gateway for advancing humanity's technological capabilities. As we've discussed, these magnetic oscillations in plasma have far-reaching implications, from understanding solar dynamics to powering future space missions. However, there are still many unanswered questions and areas of research that need to be addressed. The further we delve into the intricacies of Alfven waves, the more we realize just how much potential exists for their application. One area where Alfven waves remain a topic of intense research is in the phenomenon of cosmic rays. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. They originate from a variety of sources, including supernovae, active galactic nuclei, and even the Sun. When these particles encounter magnetic fields, They can be deflected and their trajectories altered, potentially affecting their path across the universe. Alfven waves play a significant role in the movement and acceleration of cosmic rays. As these charged particles interact with the magnetic fields and plasma, Alfven waves can cause the particles to gain additional energy and change direction. This process, known as particle acceleration, is essential for understanding the behavior of cosmic rays as they travel through space. By studying how Alfven waves influence the movement of these high-energy particles, scientists can gain a better understanding of the origins of cosmic rays and their impact on space weather. Moreover, the study of cosmic rays and their interactions with Alfven waves also has implications for understanding the nature of interstellar and intergalactic space. The presence of these high-energy particles in regions far beyond our own solar system provides valuable insights into the conditions and processes occurring in the vast, largely unexplored reaches of the universe. By analyzing how Alfven waves influence the propagation of cosmic rays, scientists can gain a better understanding of the magnetic fields that exist in these remote areas and how they shape the behavior of matter across the cosmos. In addition to cosmic rays, Alfven waves also play a critical role in the formation of shock waves in plasma. Shock waves are sudden, dramatic changes in pressure and density that occur when a disturbance, such as a supernova explosion or a stellar wind, propagates through a medium. In the context of plasma, shock waves are essential for driving the dynamics of the interstellar medium and shaping the evolution of galaxies. Alfven waves can help explain the behavior of these shock waves, particularly in the context of their role in transferring energy across vast distances. The interaction between Alfven waves and shock waves is particularly important in understanding the acceleration of particles within supernova remnants. When a star explodes in a supernova, it releases an enormous amount of energy that drives the shock waves through the surrounding plasma. These shock waves can accelerate particles to high velocities, and the presence of Alfven waves in the plasma can amplify this acceleration, allowing particles to reach even higher energies. This process contributes to the production of cosmic rays, which, as we've already discussed, are a key feature of the interstellar medium. One of the most exciting prospects of studying Alfven waves is the possibility of unlocking new methods of controlling and manipulating plasma. As we continue to develop fusion energy and advanced propulsion systems, the ability to control the behavior of plasma will become increasingly important. Alfven waves, with their ability to propagate through plasma and interact with magnetic fields, offer a unique tool for researchers looking to refine the methods for containing and stabilizing plasma in these environments. In fusion research, for example, Alfven waves could be used to stabilize the plasma in tokamaks, the donut-shaped devices used to confine plasma at the extreme temperatures and pressures required for fusion reactions. One of the challenges of fusion research is maintaining the stability of the plasma, which can easily become turbulent and chaotic. By using Alfven waves to control the motion of the plasma, researchers may be able to reduce turbulence and improve the overall efficiency of the fusion process. This, in turn, could bring us one step closer to achieving sustainable fusion energy, a breakthrough that could revolutionize energy production. In space exploration, the study of Alfven waves could also lead to advancements in plasma propulsion technologies. Plasma propulsion systems, which use magnetic fields to accelerate charged particles to high speeds, offer the potential for faster and more efficient space travel. By understanding how Alfven waves interact with plasma in these systems, engineers could refine their designs and improve the performance of spacecraft propulsion systems. This could enable long-duration missions to distant planets, moons, and even other star systems, opening up new frontiers in space exploration. But the implications of Alfven waves are not limited to these areas alone. As we continue to study the magnetic behavior of plasma, we are likely to uncover even more unexpected applications and phenomena that could reshape our understanding of the universe. From influencing the dynamics of black holes to uncovering new insights into the formation of stars and planets, the study of Alfven waves offers a glimpse into the hidden forces that govern the cosmos. Perhaps one of the most intriguing aspects of Alfven waves is their connection to the broader field of magnetohydrodynamics, MHD. MHD is the study of the behavior of electrically conductive fluids, such as plasma, in the presence of magnetic fields. It combines principles from both magnetism and fluid dynamics to explain the motion and interactions of plasma in various environments. Alfven waves are a key component of MHD theory, and their study has led to numerous discoveries in plasma physics and astrophysics. For example, MHD models that incorporate Alfven waves have been used to explain the behavior of the solar wind, the formation of sunspots, and the generation of magnetic fields in stars and galaxies. By applying MHD principles to the study of Alfven waves, scientists can simulate and predict the behavior of plasma in a wide range of environments, from the interiors of stars to the vast expanses of interstellar space. These models have been instrumental in advancing our understanding of astrophysical phenomena and have opened up new avenues of research in fields ranging from space weather forecasting to the development of new plasma technologies. Looking forward, the study of Alfven waves is likely to remain at the forefront of scientific inquiry for many years to come. As we continue to develop more advanced tools and techniques for observing and analyzing plasma, our ability to detect and study Alfven waves will only improve. With new space missions, more sophisticated laboratory experiments, and cutting-edge computational models, we are poised to uncover even deeper insights into the behavior of plasma and the magnetic forces that shape our universe. Ultimately, the study of Alfven waves represents not just a quest for knowledge, but a chance to unlock new technologies, drive advancements in space exploration, and deepen our understanding of the fundamental forces that govern the universe. From harnessing the power of these waves to improving fusion energy to exploring distant galaxies, the potential applications of Alfven waves are virtually limitless. As our understanding of these waves continues to grow, so too will our ability to shape the future of science, technology, and space exploration. As we continue to explore the vast implications of Alfven waves, one cannot help but marvel at how interconnected the study of these waves is with other areas of physics and space science. Their presence is not only a fundamental part of astrophysical phenomena but is also an exciting avenue for interdisciplinary research that bridges plasma physics, magnetism, and even quantum mechanics. One fascinating development that has recently emerged is the application of Alfven waves to the understanding of the behavior of black holes. These enigmatic objects, with their immense gravitational pull, warp the fabric of spacetime, and yet, the way they interact with surrounding plasma remains one of the greatest mysteries in modern astrophysics. Alfven waves, being an essential component of magnetized plasma, could offer insights into how black holes influence the behavior of surrounding matter, particularly in the case of accretion disks. Accretion disks are composed of plasma and dust that spiral toward a black hole, heated to extreme temperatures as they fall closer to the event horizon. The turbulence within these disks can lead to the generation of magnetic fields, and Alfven waves, as we know, are highly sensitive to these magnetic fields. In some scenarios, Alfven waves may play a significant role in the energy transfer and particle acceleration occurring in these environments. Researchers are increasingly using these waves to model the behavior of accretion disks and the dynamics of energy and matter in the vicinity of black holes. For instance, it is hypothesized that Alfven waves might assist in transferring angular momentum from the inner regions of the accretion disk to the outer regions, which could affect the rate at which matter falls into the black hole. This process, known as the accretion rate, is a crucial factor in determining the growth of black holes and the power of active galactic nuclei, AGN. By further studying the role of Alfven waves in black hole environments, scientists hope to refine their understanding of these powerful cosmic entities and their influence on surrounding space. Another area where Alfven waves play a critical role is in the behavior of stars, particularly during stellar flares. Stellar flares are sudden, explosive releases of energy from a star, and they can significantly impact the star's surrounding environment, including any planets orbiting it. These flares are often accompanied by a surge in high-energy particles, including X-rays, ultraviolet radiation, and cosmic rays. As we've seen, Alfven waves are integral to the transport of energy within plasma, and they could very well be responsible for transporting the energy released during these flares. In particular, Alfven waves may help to explain how energy from the star's core or magnetic field can reach the outer layers, leading to an eruption. By tracing the flow of these waves, scientists are working to better predict the occurrence of such flares, which can have profound effects on space weather. Stellar flares, when directed toward planets with magnetic atmospheres like Earth, could potentially disrupt communications, GPS systems, and satellite functions. The more we understand about the role Alfven waves play in these energetic bursts, the better we can anticipate and safeguard against their effects. Yet, even with all this progress, many gaps remain in our understanding of Alfven waves, and much of the research on these waves continues to be a work in progress. A critical challenge is accurately modeling their behavior in different types of plasma environments. While our current models, based on the theoretical framework of magnetohydrodynamics, MHD, provide useful insights, they are still far from perfect. For instance, MHD models typically treat plasma as a continuous, fluid-like medium, whereas real plasma is inherently a collection of charged particles that can behave in highly complex, nonlinear ways. To refine these models, researchers are looking toward more advanced techniques, including the use of numerical simulations. These simulations can model the behavior of Alfven waves in a way that takes into account the discrete nature of plasma, allowing scientists to explore how these waves propagate and interact under a variety of conditions. In turn, these simulations are expected to provide more accurate predictions of Alfven wave behavior, which will be crucial for both astrophysical studies and practical applications like fusion research and space propulsion. Furthermore, the role of Alfven waves in plasma turbulence remains an open question. Turbulence is a chaotic state of motion that can arise in plasma, causing unpredictable fluctuations in velocity, pressure, and magnetic field. The interplay between Alfven waves and plasma turbulence is not fully understood, but it is clear that these waves can either drive or be affected by turbulence. The nature of this relationship is a central focus of research in plasma physics, as it holds the key to understanding how plasma behaves in high-energy environments such as the Sun's corona or the interstellar medium. One particularly exciting prospect for future research involves using Alfven waves as a tool for diagnosing and controlling plasma behavior in experimental settings. In laboratory plasma devices such as tokamaks or stellarators, which are designed to replicate the conditions required for nuclear fusion, the ability to control plasma turbulence is essential. By using Alfven waves to manipulate and stabilize the plasma, researchers may be able to improve the confinement and efficiency of these devices, bringing us closer to achieving sustainable nuclear fusion as a viable energy source. Moreover, the study of Alfven waves has the potential to revolutionize our understanding of space weather and its effects on Earth. The Sun's activity, particularly the solar wind and coronal mass ejections (CMEs), has a direct impact on space weather, which can in turn affect satellite systems, telecommunications, and even power grids on Earth. Alfven waves may provide an important piece of the puzzle in understanding how these solar phenomena propagate through the heliosphere and interact with Earth's magnetosphere. By learning how these waves influence the transport of solar wind and energetic particles, we could develop more accurate models for predicting space weather and protecting our technological infrastructure. In a broader sense, the study of Alfven waves is also a gateway to understanding the fundamental nature of magnetized plasma, a state of matter that is ubiquitous in the universe. Whether in the fiery interior of stars, the energetic environments surrounding black holes, or the vast intergalactic void, plasma is the most common state of matter. Yet, despite its ubiquity, plasma remains one of the least understood states of matter. Alfven waves are just one of many phenomena that arise from the unique properties of plasma, and as we continue to study them, we may uncover entirely new insights into the behavior of matter and energy on cosmic scales. The future of Alfven wave research is both exciting and uncertain. As new telescopes, space probes, and computational methods emerge, scientists will have access to more data and better tools for studying these waves in their natural environments. Whether it's probing the dynamic behavior of the Sun, understanding the magnetized regions around black holes, or exploring the origins of cosmic rays, Alfven waves are likely to remain a central topic of scientific inquiry for years to come. Alfven waves are far more than just magnetic oscillations in plasma. They are a fundamental part of the dynamic processes that shape the universe. From their role in star formation to their impact on space weather, these waves offer a window into the complex interactions that govern cosmic phenomena. As we continue to study and understand Alfven waves, we are not only uncovering the secrets of the universe but also advancing our technology, making strides in energy production, and improving our ability to explore the cosmos. The more we learn about these waves, the closer we get to unlocking some of the deepest mysteries of space. As we delve deeper into the intricacies of Alfven waves, it becomes apparent that they are not just an isolated feature of plasma physics but rather a key element that connects various phenomena across the universe. Their ability to influence and interact with the environment surrounding stars, black holes, and galaxies provides scientists with invaluable insights into the complex workings of the cosmos. However, the true power of Alfven waves lies in their potential to uncover even more mysterious aspects of space, such as the behavior of dark matter, the properties of dark energy, and the dynamics of exotic cosmic objects. One intriguing possibility is the role Alfven waves might play in explaining the distribution and behavior of dark matter in galaxies. Dark matter, which makes up roughly 27% of the universe's mass, interacts only via gravity and possibly weak forces, making it incredibly difficult to detect directly. However, its gravitational influence on visible matter, such as stars and gas, suggests that it plays a vital role in the formation and evolution of galaxies. Recent research has proposed that Alfven waves, through their ability to propagate energy and influence plasma in intergalactic space, could potentially interact with dark matter in a way that might reveal more about its nature. This theory is still in its infancy, and more observations and modeling are needed, but it opens up an entirely new avenue for understanding dark matter. By studying the ways Alfven waves might interact with both plasma and dark matter, astrophysicists hope to find indirect evidence that could finally shed light on the elusive nature of this mysterious substance. Similarly, dark energy, the mysterious force that drives the accelerated expansion of the universe, may also have a connection to Alfven waves. While dark energy remains one of the most puzzling aspects of cosmology, scientists have hypothesized that its influence might be detectable through its interaction with plasma fields. If Alfven waves are indeed influenced by dark energy, then studying their behavior could offer indirect evidence of this force and provide a deeper understanding of the universe's expansion. The potential connections between Alfven waves, dark energy, and dark matter are some of the most exciting prospects in modern physics, and further research in these areas could lead to groundbreaking discoveries. In addition to their potential links to dark matter and dark energy, Alfven waves may also help us understand some of the most extreme and enigmatic objects in the universe, such as neutron stars and pulsars. Neutron stars, which are remnants of massive stars that have exploded in supernovae, are among the densest objects in the universe, with magnetic fields that can be trillions of times stronger than Earth's. These powerful magnetic fields interact with the surrounding plasma, creating conditions where Alfven waves could have a significant impact. In fact, some researchers have proposed that Alfven waves could be responsible for the high-energy emissions observed in pulsars, the rapidly rotating neutron stars that emit beams of radiation. As these waves propagate through the plasma surrounding the pulsar, they could contribute to the acceleration of particles to near-light speeds, producing the intense radiation that makes pulsars so distinctive. By studying the Alfven wave interactions in these extreme environments, scientists hope to gain a better understanding of the internal structure of neutron stars and the mechanisms behind their powerful emissions. Alfven waves are also deeply intertwined with the study of space weather, which, while not as exotic as black holes or pulsars, plays a crucial role in shaping the environment of our own solar system. Space weather, driven by the sun's activity, includes phenomena like solar flares, coronal mass ejections, CMEs, and solar wind, all of which can have a direct impact on Earth's technological infrastructure. By understanding the role of Alfven waves in the transmission of energy and particles through the solar system, researchers can improve space weather models, which in turn will enhance our ability to predict and mitigate the effects of solar storms. In particular, the role of Alfven waves in solar wind dynamics is of great importance. Solar wind, a stream of charged particles released from the sun's corona, can carry Alfven waves through space, affecting the magnetospheres of planets and moons. These waves can influence the way solar wind interacts with the Earth's magnetic field, leading to phenomena like auroras. However, Alfven waves may also play a role in more disruptive events, such as geomagnetic storms, which can damage satellites, interfere with GPS systems, and even cause power outages. By studying the interactions between Alfven waves and the solar wind, scientists hope to develop better forecasting tools to protect Earth from the potentially harmful effects of space weather. The study of Alfven waves also has significant implications for the field of plasma physics, particularly when it comes to controlled fusion research. Fusion, the process by which atomic nuclei combine to release energy, holds the promise of a nearly limitless and clean energy source. However, achieving controlled fusion on Earth requires replicating the extreme temperatures and pressures found in the cores of stars. Plasma, the fourth state of matter, is essential for fusion reactions, and understanding how Alfven waves influence plasma behavior is crucial for improving fusion reactor designs. In fusion reactors, such as tokamaks or stellarators, magnetic fields are used to contain the plasma and prevent it from touching the reactor walls. However, plasma is inherently unstable, and disturbances can lead to loss of confinement and decreased performance. Alfven waves, with their ability to transport energy and momentum across plasma, could potentially be used to control these instabilities. By understanding how Alfven waves propagate through the plasma in these reactors, scientists hope to develop methods for stabilizing the plasma and increasing the efficiency of fusion reactions. This research could be a key step toward making fusion energy a viable and sustainable source of power. Moreover, as we look beyond our own solar system, the role of Alfven waves in shaping the interstellar medium and the formation of stars and galaxies becomes even more fascinating. The interstellar medium, the vast and largely empty space between stars, is filled with low-density gas and plasma. Alfven waves may play a critical role in the dynamics of this medium, particularly in the processes of star formation. The compression and heating of plasma due to Alfven waves could contribute to the creation of new stars, providing the energy needed to initiate nuclear fusion. Similarly, Alfven waves might also play a role in the larger-scale dynamics of galaxies. The magnetic fields in galaxies interact with the plasma that permeates the galactic space, and Alfven waves could be a key driver of the motion and behavior of this plasma. Understanding how these waves influence the dynamics of galaxies could shed light on the mechanisms behind galaxy formation and evolution, and even help us understand the behavior of massive cosmic structures like galaxy clusters. As we continue to explore the role of Alfven waves in these diverse cosmic environments, it becomes clear that they are much more than a mere curiosity of plasma physics. They are a fundamental piece of the puzzle in understanding the universe itself. From their impact on the sun's corona to their potential influence on dark matter, Alfven waves are opening new doors to understanding the forces that govern the cosmos. The future of Alfven wave research holds immense promise. With advancements in observational technologies, such as space-based telescopes and advanced particle detectors, and improvements in computational simulations, scientists are poised to uncover even more about these magnetic oscillations. As we continue to push the boundaries of our knowledge, Alfven waves will undoubtedly remain a critical area of research in both theoretical and experimental physics. The study of Alfven waves is one of the most fascinating and complex areas of modern astrophysics. These waves, which propagate through magnetized plasma, are not only central to the dynamics of stars, galaxies, and black holes, but they also hold the key to understanding some of the most fundamental mysteries of the universe. From space weather to the nature of dark matter, Alfven waves provide a unique perspective on the forces that shape the cosmos. As we continue to explore these waves and their interactions with plasma, we will undoubtedly make new discoveries that challenge our understanding of the universe and open up new frontiers of knowledge. The interconnectedness of Alfven waves with nearly every aspect of plasma dynamics reveals their significance as a bridge between the observable universe and the hidden forces that govern it. But what makes these waves so unique is their ability to exist and propagate within the magnetic fields of plasma-dominated environments. These oscillations not only carry energy across vast distances but also serve as diagnostic tools, allowing scientists to probe otherwise inaccessible regions of space. In Earth's magnetosphere, for example, Alfven waves are essential for understanding how solar wind interacts with our planet's magnetic field. This interaction forms a protective barrier known as the magnetosphere, which shields Earth from harmful cosmic and solar radiation. However, when Alfven waves carry enough energy through the magnetosphere, they can destabilize this barrier, creating auroras and sometimes even geomagnetic storms. These storms, while stunning to observe, pose significant risks to satellites, electrical grids, and modern communication systems. On a more granular level, Alfven waves help scientists decode the structure and strength of magnetic fields in space. The properties of these waves, such as their speed, frequency, and amplitude, depend on the density of the plasma and the strength of the magnetic field they traverse. By analyzing these properties, scientists can infer the conditions in environments millions of miles away, whether it's the Sun's corona, the interstellar medium, or even distant galaxies. This non-invasive, remote sensing capability makes Alfven waves a powerful tool in astrophysics. Moreover, Alfven waves are indispensable in the study of magnetohydrodynamics, MHD, the field of physics that explores the behavior of electrically conducting fluids, like plasmas, in the presence of magnetic fields. MHD equations, which describe the motion and dynamics of such fluids, often include terms that account for the propagation of Alfven waves. These waves serve as a cornerstone for modeling astrophysical phenomena, from the turbulent motions of plasma around black holes to the behavior of cosmic jets that stretch across intergalactic space. One of the most exciting developments in recent years has been the discovery of Alfvenic turbulence, a state in which Alfven waves interact with one another, creating a chaotic and energy-rich environment. This turbulence is thought to be a key mechanism for heating plasma in regions like the Sun's corona, where temperatures inexplicably soar to millions of degrees far hotter than the Sun's surface. By studying Alfvenic turbulence, scientists are piecing together the puzzle of coronal heating, one of the longest-standing mysteries in solar physics. But the importance of Alfven waves doesn't stop at heating plasma. Their role in particle acceleration is equally crucial. In high-energy astrophysical environments, such as supernova remnants, or the surroundings of pulsars, Alfven waves can transfer their energy to charged particles, accelerating them to near-light speeds. These accelerated particles, known as cosmic rays, can travel across the universe and eventually reach Earth, where they provide valuable information about their origins and the conditions of the interstellar medium. Another frontier where Alfven waves are making an impact is the study of exoplanetary magnetospheres. With the discovery of thousands of exoplanets orbiting stars other than the Sun, understanding their magnetic environments has become a priority. Alfven waves could serve as a diagnostic tool for assessing the strength and behavior of these magnetic fields, offering clues about the habitability of these distant worlds. A planet's magnetic field, much like Earth's, plays a crucial role in protecting its atmosphere from being stripped away by stellar winds. If Alfven waves can be detected in these systems, they could provide indirect evidence of magnetic activity and, by extension, the potential for life. The connection between Alfven waves and magnetic reconnection is another fascinating area of study. Magnetic reconnection occurs when opposing magnetic field lines in plasma break and reconnect, releasing immense amounts of energy. This process powers events like solar flares and coronal mass ejections, which can have significant impacts on Earth. Alfven waves are thought to play a role in triggering or stabilizing magnetic reconnection, making them a key piece of the puzzle in understanding these dynamic processes. On a cosmic scale, Alfven waves could also shed light on the enigmatic cosmic magnetic fields that thread through galaxies and galaxy clusters. These fields, though weak compared to those on smaller scales, are pervasive and play a critical role in shaping the structure and evolution of the universe. How these magnetic fields form and sustain themselves is a question that has puzzled scientists for decades. Alfven waves, by transporting energy and momentum across these vast scales, might be a crucial mechanism in maintaining these fields. In addition to their astrophysical implications, Alfven waves have practical applications closer to home. For instance, understanding how they propagate in plasma has direct implications for the design and operation of space missions. Satellites and spacecraft that venture into the plasma-rich environments of the Sun or the magnetospheres of other planets must contend with the effects of Alfven waves. By predicting these interactions, engineers can design more robust systems to ensure the success of these missions. As research on Alfven waves continues, new technologies are emerging to study them more effectively. Instruments aboard spacecraft like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are providing unprecedented data on the behavior of plasma and magnetic fields in the solar environment. These missions are already yielding insights into how Alfven waves contribute to solar wind acceleration and coronal heating, paving the way for future discoveries. In parallel, advancements in computational modeling are allowing scientists to simulate the behavior of Alfven waves in complex environments with remarkable accuracy. These simulations are not only helping to interpret observational data but also enabling researchers to test theoretical models in ways that were previously impossible. As computing power continues to grow, so too will our ability to unravel the mysteries of Alfven waves and their role in the universe. The journey to understand Alfven waves is far from over. Each new discovery raises more questions than it answers, driving the field forward in exciting and unexpected directions. From their role in the smallest scales of plasma physics to their influence on the largest structures in the universe, Alfven waves are a testament to the interconnectedness of nature. They remind us that even the most subtle phenomena can have profound implications, shaping our understanding of the cosmos and our place within it. The story of Alfven waves and their vast implications is a reminder of the intricate tapestry that governs the universe, where seemingly minor oscillations can ripple outwards, shaping cosmic phenomena on scales both small and incomprehensibly large. As we delve deeper into the subject, it becomes clear that these magnetic oscillations are not merely confined to theoretical equations or distant astrophysical systems. They have a tangible impact on our understanding of the universe and, by extension, our daily lives. For instance, the study of Alfven waves provides critical insights into space weather forecasting. Solar storms and coronal mass ejections (CMEs), driven in part by magnetic reconnection and turbulence involving Alfven waves, can disrupt Earth's magnetosphere and ionosphere. This disruption can interfere with GPS signals, communication networks, and even power grids, causing widespread technological and economic consequences. By understanding how Alfven waves propagate and interact within the Sun's corona and interplanetary space, scientists can improve predictive models, giving humanity a better chance to prepare for such events. One particularly fascinating application of Alfven wave research is in the realm of controlled nuclear fusion. Fusion, the process that powers stars, holds the potential to provide a virtually limitless and clean source of energy for humanity. Magnetic confinement fusion devices, like tokamaks, rely on strong magnetic fields to contain hot plasma where fusion reactions occur. Alfven waves play a critical role in the behavior of this plasma. They can transport energy, redistribute particles, and influence instabilities that might otherwise disrupt the fusion process. By studying Alfven waves, researchers aim to develop more stable and efficient methods for achieving sustained fusion, bringing humanity one step closer to unlocking the energy of the stars. The connection between Alfven waves and turbulence continues to be a hotbed of research, especially in the context of astrophysical jets and accretion disks. These phenomena occur near black holes, neutron stars, and other compact objects, where extreme gravitational forces create swirling disks of matter. Alfven waves are thought to be a key component in the transfer of angular momentum within these systems, allowing matter to spiral inward toward the central object while simultaneously enabling jets of high-energy particles to be ejected at near-light speeds. These jets, visible across vast cosmic distances, serve as beacons that reveal the presence of some of the universe's most enigmatic objects. Further afield, Alfven waves are also crucial for understanding galactic evolution. In the interstellar medium, where gas and magnetic fields intermingle, these waves contribute to the transport of energy and momentum across vast distances. They influence processes like star formation by regulating the collapse of gas clouds under gravity. Without the damping effects of Alfven waves, the dynamics of these clouds would be vastly different, potentially altering the rate and nature of star formation throughout galaxies. Even in the vast, empty expanse of intergalactic space, Alfven waves might play a subtle yet significant role. The tenuous plasma that exists between galaxies is threaded with weak magnetic fields, and these fields are thought to interact with waves like those described by Alfven. Such interactions could contribute to the large-scale structure of the universe, influencing the distribution of matter and the dynamics of galaxy clusters. As our observational tools improve, so too does our ability to study these waves in environments that were previously inaccessible. Instruments capable of detecting minute changes in magnetic fields, plasma density, and wave propagation are opening new windows into the behavior of Alfven waves across the cosmos. For instance, the upcoming James Webb Space Telescope and other advanced observatories may enable indirect studies of these waves in distant star-forming regions or even around exoplanets with strong magnetospheres. In parallel, the theoretical framework surrounding Alfven waves is evolving. Researchers are exploring the nonlinear dynamics of these waves, including how they interact with each other and with their surroundings. These interactions can lead to complex phenomena, such as wave coupling, resonance, and energy cascades, which are vital for understanding the overall behavior of plasma systems. Such studies not only deepen our understanding of fundamental physics, but also have practical implications for everything from space exploration to energy production. The interdisciplinary nature of Alfven wave research means that discoveries in one area often have ripple effects in others. For example, advancements in computational modeling of plasma behavior in laboratory settings can inform our understanding of solar physics, while observations of Alfven waves in space can provide insights that improve terrestrial technologies. This interconnectedness underscores the universal relevance of Alfven waves, transcending the boundaries of traditional scientific disciplines. As we look to the future, one of the most exciting prospects is the potential for Alfven waves to unlock new mysteries in the search for extraterrestrial life. Magnetic fields and plasma dynamics are likely to play a crucial role in shaping the environments of habitable worlds, both within our solar system and beyond. By studying how Alfven waves influence these environments, scientists may be able to identify key signatures that point to the presence of life or the conditions necessary for it to thrive. Ultimately, the study of Alfven waves is a testament to the power of curiosity and the human drive to understand the universe. What began as a theoretical prediction by Hannes Alfven has blossomed into a rich field of research that touches nearly every aspect of astrophysics, space science, and plasma physics. These waves, oscillating through the magnetic fabric of the cosmos, remind us of the profound interconnectedness of all things and the endless potential for discovery. The story of Alfven waves is far from over. Each new observation, experiment, and theory adds another layer to our understanding, drawing us closer to the fundamental truths that govern the universe. And as we continue to explore, these magnetic oscillations will undoubtedly remain a guiding light, illuminating the path toward deeper knowledge and greater wonder. The journey of understanding Alfven waves doesn't just end with theoretical exploration or practical applications. Their implications extend to some of the most profound questions about the nature of the universe, the origins of cosmic phenomena, and the ultimate fate of everything we observe. These magnetic oscillations, seemingly simple at first glance, are deeply woven into the dynamics of matter, energy, and the interplay between the two. One particularly tantalizing area of exploration is how Alfven waves might influence the behavior of dark matter and dark energy, two of the most mysterious components of the universe. While dark matter interacts primarily through gravity and has yet to be directly observed, there are hypotheses suggesting it could have subtle electromagnetic interactions under specific conditions. If such interactions exist, Alfven waves could serve as a conduit for studying them, potentially offering clues about the elusive properties of dark matter. Similarly, understanding how magnetic fields and plasma dynamics, including Alfven waves, operate on cosmological scales might indirectly shed light on the role dark energy plays in the accelerating expansion of the universe. The influence of Alfven waves on cosmic magnetism also opens up questions about the origins of magnetic fields themselves. Magnetic fields are ubiquitous, threading through galaxies, stars, and interstellar and intergalactic plasma, but their genesis remains one of the great mysteries of astrophysics. Did they arise from primordial fluctuations shortly after the Big Bang, or were they generated later through processes like turbulent dynamo mechanisms? Alfven waves, by interacting with and propagating through magnetic fields, could hold key information about their origins and evolution. By studying these waves, scientists hope to unravel the history of cosmic magnetism and understand how it has shaped the universe. Closer to home, Alfven waves also offer insights into planetary magnetospheres and their interactions with solar wind. For instance, Earth's magnetosphere is a protective bubble that shields the planet from harmful solar radiation and charged particles. Alfven waves generated within this magnetosphere play a role in auroral displays, such as the northern and southern lights. These waves transport energy and particles along magnetic field lines, creating stunning visual phenomena and influencing the dynamics of Earth's upper atmosphere. Similarly, studying Alfven waves around other planets, like Jupiter and Saturn, can provide a comparative perspective on how magnetospheres vary across the solar system. The connection between Alfven waves and planetary magnetospheres extends to exoplanet research as well. Many exoplanets orbit stars with strong magnetic activity, and their atmospheres and potential habitability could be shaped by interactions with stellar winds and magnetic fields. Alfven waves might serve as diagnostic tools for assessing these interactions, helping researchers identify planets with stable environments that could support life. In the broader context of space exploration, understanding Alfven waves could also improve spacecraft design and navigation. Spacecraft traveling through plasma-rich environments, such as the solar wind or planetary magnetospheres, are subjected to electromagnetic forces and particle fluxes influenced by these waves. By anticipating and mitigating the effects of Alfven waves, engineers can enhance spacecraft durability and operational efficiency, paving the way for more ambitious missions to explore the far reaches of our solar system and beyond. Furthermore, Alfven waves are central to understanding the processes that govern the solar corona and the solar wind. The corona, the Sun's outer atmosphere, is puzzlingly hotter than the Sun's surface, a phenomenon known as the coronal heating problem. Alfven waves are one of the leading explanations for this enigma. These waves can carry vast amounts of energy from the Sun's interior to its outer layers, where their dissipation heats the plasma to millions of degrees. By unraveling this process, scientists can gain deeper insights into the mechanisms driving solar activity and its impact on the heliosphere, the vast bubble of space influenced by the Sun's magnetic field. The role of Alfven waves in the solar wind is equally fascinating. As these waves propagate through the solar wind, they contribute to its acceleration and structure, influencing how it interacts with planetary magnetospheres and interstellar space. Understanding this dynamic is essential for predicting and mitigating the effects of space weather, as well as for studying the boundaries of the heliosphere, where the solar wind meets the interstellar medium. Alfven waves also provide a unique lens for exploring the high-energy environments around compact objects like neutron stars and black holes. These regions are dominated by intense magnetic fields and relativistic plasma, where the interplay of gravity, magnetism, and particle dynamics creates some of the most extreme phenomena in the universe. Alfven waves can mediate energy transfer, influence particle acceleration, and contribute to the formation of powerful jets and outflows. By studying these waves, scientists hope to unlock the secrets of these enigmatic objects and their role in cosmic evolution. As technology advances, so too does our ability to study Alfven waves in greater detail. Instruments like magnetometers and plasma analyzers on spacecraft, along with ground-based observatories, are providing unprecedented data on magnetic and plasma dynamics. These observations, combined with sophisticated simulations and theoretical models, are allowing researchers to explore the full complexity of Alfven waves and their interactions with their surroundings. Looking to the future, the study of Alfven waves is likely to intersect with emerging fields like quantum magnetohydrodynamics, QMHD, and quantum plasma physics. These disciplines aim to bridge the gap between classical plasma physics and quantum mechanics, exploring how quantum effects might influence wave behavior in extreme environments. Such research could open new frontiers in our understanding of the universe, revealing phenomena that are currently beyond the reach of classical theories. Alfven waves are more than just a scientific curiosity. They are a testament to the interconnectedness of the universe. From the microscopic scales of laboratory plasma experiments to the vast expanses of interstellar and intergalactic space, these waves demonstrate how simple physical principles can manifest in complex and unexpected ways. They remind us that even the most subtle phenomena can have profound implications, shaping the cosmos in ways we are only beginning to comprehend. The story of Alfven waves is far from complete. With each new discovery, we come closer to understanding the intricate dance of magnetic fields, plasma, and waves that governs the universe. And as we continue to explore, these oscillations will remain a guiding force, inspiring curiosity, advancing knowledge, and deepening our connection to the cosmos. The exploration of Alfven waves continues to open doors to mysteries that transcend our current understanding, bridging gaps between disciplines and inspiring innovation in science and technology. As we delve deeper into their role in the cosmos, their practical applications also expand, ranging from advancements in energy production to revolutionizing space travel. One area where Alfven waves hold transformative potential is in the development of fusion energy. Fusion, the process that powers stars, relies on the containment and manipulation of plasma, conditions where Alfven waves are inherently present. The complex interaction of magnetic fields and plasma oscillations can either enhance or hinder the stability of a fusion reaction. By understanding and harnessing Alfven waves, scientists aim to create more efficient and stable fusion reactors, which could provide a virtually limitless and clean energy source for humanity. The study of these waves in the context of controlled fusion experiments, such as tokamaks and stellarators, is already shedding light on how to optimize plasma confinement and energy output. On a cosmic scale, Alfven waves play a pivotal role in the formation and behavior of galactic structures. Magnetic fields within galaxies are intricately tied to plasma dynamics, shaping the flow of matter and energy across vast distances. These waves influence the motion of interstellar gas, facilitating processes like star formation and the aggregation of matter into galaxies. By studying these interactions, astronomers can better understand the life cycles of galaxies, from their initial formation to their eventual evolution and, in some cases, their collision and merger with other galaxies. In regions like the Milky Way's spiral arms, where dense molecular clouds collapse to form stars, Alfven waves propagate through magnetic fields, impacting the rate and efficiency of star formation. These waves can either compress gas clouds to trigger gravitational collapse or disperse them, depending on the interplay of forces. This dual role makes Alfven waves a critical factor in shaping the stellar population of galaxies and determining their overall structure. Beyond individual galaxies, Alfven waves are also believed to influence the behavior of galaxy clusters, the largest gravitationally bound structures in the universe. These clusters are permeated by hot plasma and magnetic fields, creating an environment where Alfven waves can propagate on massive scales. Their interactions with magnetic turbulence and relativistic particles contribute to phenomena like radio halos and relics, which are key observational features of galaxy clusters. By examining these features, scientists can gain insights into the large-scale distribution of matter and energy in the cosmos. Another intriguing aspect of Alfven waves is their potential role in the mysterious phenomenon of cosmic rays. These high-energy particles, which originate from sources like supernovae, black holes, and even distant galaxies, traverse the universe at nearly the speed of light. As they travel, cosmic rays interact with magnetic fields and plasma, processes that are heavily influenced by Alfven waves. These interactions can accelerate cosmic rays, change their trajectories, or even create new particle cascades, shaping the composition and behavior of these enigmatic travelers. Understanding these processes not only helps us unravel the origins of cosmic rays but also provides a deeper perspective on the energetic dynamics of the universe. On Earth, the study of Alfven waves offers practical benefits for space weather prediction and mitigation. Space weather events, such as solar flares and coronal mass ejections, CMEs, can have severe impacts on satellites, power grids, and communication systems. These events are driven by the dynamics of the Sun's magnetic field and plasma, where Alfven waves play a crucial role. By monitoring these waves and their interactions with the solar wind, scientists can develop more accurate models for predicting space weather, helping to protect critical infrastructure and human activities in space. The ability to predict and respond to space weather is particularly important as humanity ventures deeper into space. Missions to the Moon, Mars, and beyond will require robust systems to shield astronauts and equipment from the harmful effects of radiation and charged particles. Alfven waves, as mediators of energy and particle transport in plasma, will be a key focus of research aimed at designing safer and more resilient spacecraft and habitats. Meanwhile, the role of Alfven waves in star formation offers profound implications for the search for extraterrestrial life. Stars are the birthplaces of planets, and the conditions under which they form can influence the likelihood of habitable worlds. By studying how Alfven waves shape star-forming regions and their magnetic environments, scientists can identify the factors that contribute to the emergence of planetary systems with stable, life-supporting conditions. In the realm of fundamental physics, Alfven waves serve as a testing ground for theories that extend beyond classical electrodynamics and magnetohydrodynamics. For instance, they provide a natural context for exploring the effects of relativistic speeds and quantum phenomena in plasma. These investigations could lead to breakthroughs in our understanding of high-energy astrophysical processes and the fundamental forces that govern the universe. The study of Alfven waves is also influencing emerging technologies on Earth. Concepts like plasma propulsion for spacecraft, advanced particle accelerators, and even medical applications of plasma are benefiting from the insights gained from studying these waves. In plasma propulsion, for example, Alfven waves can enhance the efficiency and control of ionized gas used to generate thrust, potentially enabling faster and more economical space travel. As we continue to unravel the mysteries of Alfven waves, one thing becomes clear. They are not just an isolated phenomenon but a unifying thread that connects diverse aspects of the universe. From the tiniest laboratory plasma experiments to the grandest cosmic structures, these magnetic oscillations reveal the intricate interplay of forces that shape our reality. The journey of discovery is far from over. With each new observation and experiment, we deepen our understanding of Alfven waves and their role in the cosmos. And as we push the boundaries of knowledge, these waves will remain a source of inspiration, driving innovation, expanding our horizons, and reminding us of the beauty and complexity of the universe. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.